Welcome back. Tonight, we settle in with the patient, painstaking work of astronomers who, across centuries and with instruments both humble and magnificent, have stretched their measuring tapes toward the stars, beginning with the ancient Greeks, who used shadows and geometry to gauge the moon's distance, and continuing through the era of parallax observations, standard candles, and the gentle redshift of retreating galaxies, each method building upon the last like rungs on an infinite ladder reaching into the dark. Before we begin, take a moment to like the video and subscribe, but only if these stories help you drift off peacefully. Now, dim the lights. Pull the blanket a little closer. And together, let us ease gently into tonight's story. Let us begin, then, at the very start of this long and patient endeavor, in those distant centuries when human beings first turned their minds, with something like systematic care, to the question of how far away the heavenly bodies might actually be. It is worth settling in here, letting the breath slow, because these ancient attempts to measure the cosmos unfold at their own quiet pace, and there is something deeply restful in following the thoughts of people who lived more than 2,000 years ago as they tried, with nothing but their eyes and their geometry and the unhurried movements of shadows, to understand the size of the universe that held them. In the ancient world, the sky was not merely a subject of idle curiosity but a matter of profound philosophical and practical importance, and yet for all the attention that early thinkers gave to the motions of the stars and planets, the actual distances involved remained, for the most part, beyond serious consideration. The heavens were understood to be far away in some general sense, certainly beyond human reach, but the question of precisely how many stadia or parasangs separated the Earth from the Moon, or the Moon from the Sun, was not one that most philosophers felt equipped to answer with any confidence. There were, however, a handful of remarkable individuals who believed that geometry, that most elegant and reliable of human tools, might allow them to extend their measurements beyond the surface of the Earth and out into the celestial realm, and it is to these patient observers that we now turn our attention. Aristarchus of Samos, who lived from approximately 310 to 230 years before the Common Era, was one of the first to attempt a geometric measurement of cosmic distances, and his method remains, even today, a beautiful example of how far careful reasoning can take us when we have only the simplest of observations to work with. Aristarchus understood that the moon passes through the shadow of the Earth during a lunar eclipse, and he realized that by observing the size of the Earth's shadow relative to the moon, and by making certain assumptions about the geometry of the Sun, Earth, and Moon system, he could estimate how far away the moon must be. His reasoning was intricate but not impossibly so, involving considerations of the angle at which we see the Sun and the time it takes for the moon to cross through Earth's shadow, and when he had worked through all of his calculations, he arrived at a figure of roughly 60 Earth radii for the distance to the moon. This number, achieved more than 2 millennia ago with nothing but patient observation and the power of geometric thinking, is remarkably close to the value we accept today, which is approximately 60.3 Earth radii. There is something quietly wonderful in this, and something restful too, in knowing that a person sitting on a Mediterranean island so very long ago, watching the slow creep of shadow across the lunar face, could arrive at a truth that has held firm across all the intervening centuries. Of course, Aristarchus faced a significant limitation, one that would constrain all ancient attempts to measure cosmic distances, and this was the fundamental problem of not knowing, with any precision, the actual size of the Earth itself. To say that the moon lies at a distance of 60 Earth radii is meaningful only if one knows how large an Earth radius actually is, and in the time of Aristarchus, this value was not yet established with any reliability. It would fall to another patient observer, working in the remarkable intellectual environment of Hellenistic Egypt, to provide the first truly accurate measurement of our planet's circumference. Eratosthenes of Cyrene, who lived from approximately 276 to 194 years before the Common Era, served as the chief librarian of the Great Library at Alexandria, and it was there, surrounded by the accumulated knowledge of the ancient world, that he devised his famous method for measuring the Earth. The story, which has been told many times but never grows less satisfying in its elegant simplicity, begins with a well in the town of Syene, located in southern Egypt near what is now Aswan. Eratosthenes had learned, perhaps from travelers or from reports in the library's collection, that on the day of the summer solstice, the sun at noon shone directly down into a deep well at Syene, illuminating the water at the bottom without casting any shadow on the walls. This meant that at Syene, on that particular day, the sun was positioned directly overhead. In Alexandria, however, which lay some considerable distance to the north, the sun at the same moment was not directly overhead but rather cast a small shadow, and by measuring the angle of this shadow, Eratosthenes could determine the difference in latitude between the two cities. He found that the angle was approximately 1/50th of a full circle, which is to say about 7 degrees, and since he knew, or could estimate, the distance between Syene and Alexandria to be roughly 5,000 stadia, he could calculate the full circumference of the Earth by multiplying this distance by 50. His result was approximately 250,000 stadia, which, depending on the precise length of the stadion he was using, corresponds to somewhere in the neighborhood of 40,000 kilometers. The modern accepted value for Earth's circumference at the equator is just over 40,000 kilometers, and so Eratosthenes, working with the simplest of tools and the most patient of methods, achieved an accuracy that still commands quiet admiration. With the size of the Earth now established, at least approximately, the lunar distance estimated by Aristarchus could be converted into more tangible terms, and the cosmos began, slowly, to take on a measurable scale. But there was still much work to be done, and the next significant figure in this gentle history is Hipparchus, who lived from approximately 190 to 120 years before the Common Era and who is sometimes called the greatest astronomer of antiquity. Hipparchus made many contributions to the understanding of the heavens, including the discovery of the precession of the equinoxes and the creation of the first comprehensive star catalogue. But for our purposes here, in this quiet consideration of cosmic distances, his most relevant achievement was the refinement of the lunar distance measurement using the method of parallax. Parallax is the apparent shift in the position of a nearby object when viewed from two different locations, and Hipparchus realized that a solar eclipse, which occurs when the moon passes between the Earth and the Sun, would appear slightly different to observers at different places on Earth. By gathering reports of a solar eclipse as observed from two widely separated locations, and by carefully comparing the degree to which the moon obscured the sun at each site, Hipparchus could calculate the parallax of the moon and thus its distance. His results confirmed and refined the earlier estimate of Aristarchus, establishing the lunar distance at roughly 60 Earth radii, and this value would remain the accepted figure throughout antiquity and well into the medieval period. Meanwhile, in the distant east, other patient observers were making their own contributions to the understanding of the heavens. Zhong Heng, a Chinese polymath who lived from 78 to 139 years of the Common Era, made significant advances in astronomical instrumentation, including the development of a refined armillary sphere that allowed for more precise observations of celestial positions. The armillary sphere, a framework of graduated rings representing the celestial equator, the ecliptic, and other important circles of the sky, enabled observers to track the movements of the sun, moon, and stars with greater accuracy than had previously been possible. While Zhong Heng's work did not directly yield new measurements of cosmic distances in the manner of Aristarchus or Hipparchus, his instruments and methods contributed to a growing tradition of careful positional astronomy in China, one that would continue to develop over the following centuries and would eventually engage with questions of cosmic scale in its own distinctive ways. There is something restful in contemplating these parallel traditions, East and West, each in its own manner striving to understand the architecture of the universe, each constrained by similar limitations and yet each contributing something valuable to the slow accumulation of human knowledge. In the Mediterranean world, the culmination of ancient astronomical knowledge came with Claudius Ptolemy, who lived and worked in Alexandria during the 2nd century of the Common Era and whose great work, the Almagest, would serve as the definitive astronomical textbook for more than 1,000 years. Ptolemy codified and systematized the work of his predecessors, including the distance measurements of Aristarchus and Hipparchus, and he presented a comprehensive model of the cosmos in which the Earth sat motionless at the center, surrounded by a series of nested crystalline spheres carrying the moon, the sun, the planets, and finally the fixed stars. The Almagest gave specific values for the distances to each of these celestial bodies, expressed in terms of Earth radii, and while many of Ptolemy's figures were significantly in error, particularly his estimate of the solar distance, which was far too small, his work nonetheless represented the most complete and systematic attempt yet made to assign numerical values to the scale of the universe. And yet, for all their ingenuity and patience, the ancient astronomers were constrained by limitations both practical and philosophical. On the practical side, there remained the difficulty of measuring very small angles with sufficient precision, a problem that would not be fully overcome until the development of telescopic instruments many centuries later. But perhaps more significant, in some ways, was the philosophical resistance to the idea of a truly vast cosmos, a resistance that arose from deeply held beliefs about the nature of the universe and humanity's place within it. In many ancient worldviews, both Greek and otherwise, the cosmos was understood as a finite and relatively compact structure, designed with human beings as its central concern. The stars were not unimaginably distant suns, but rather luminous points fixed to a celestial sphere that lay just beyond the orbit of Saturn. The universe, in this conception, was measured in thousands or tens of thousands of Earth radii, not in the millions of kilometers that we now know to be the true scale. Religious and philosophical cosmologies often reinforced this sense of a bounded, human-scaled universe. The heavens were the realm of the divine, perfect and unchanging, fundamentally different in nature from the imperfect and changeable sublunary world, and there was a certain comfort in the notion that the entire cosmic structure was not so very much larger than the Earth itself. To suggest that the distances involved might be vastly greater, that the stars might be scattered across gulfs of space so immense as to be essentially incomprehensible, would have been to challenge not merely a scientific assumption but a deeply rooted understanding of what the universe was for and what place humanity occupied within it. And so, even as the geometric methods of Aristarchus and Hipparchus demonstrated that distances in the heavens could, in principle, be measured, there remained a reluctance to push those measurements beyond certain comfortable bounds, a reluctance that would persist, in various forms, for many centuries to come. We may rest here for a moment, then, with these first glimmers of cosmic measurement, these early attempts to extend the reach of human knowledge beyond the familiar surface of the Earth and out into the silent depths of space. The methods were simple, the tools were crude by later standards, and the results, while sometimes remarkably accurate, were limited by both the available technology and the prevailing assumptions about what kind of universe we inhabit. But the fundamental insight had been achieved, the recognition that geometry, that patient art of angles and proportions, could serve as a bridge between the human and the cosmic, allowing us to measure distances that we could never hope to traverse. This insight would lie at the heart of all subsequent attempts to chart the scale of the heavens, from the Renaissance astronomers who would soon refine these methods to the modern observers who would extend them to the farthest reaches of the observable universe. For now, though, let us simply appreciate the quiet persistence of those ancient thinkers, working by lamplight and starlight, measuring shadows and angles, and slowly, carefully, beginning to map the immensity that surrounded them. In the year 1543, an elderly Polish canon named Nicolaus Copernicus lay on his deathbed in the town of Frauenburg, and it is said that a freshly printed copy of his life's work was placed into his hands on the very day he died, though whether he was conscious enough to comprehend this final gift remains a gentle mystery lost to time. The book was called De Revolutionibus Orbium Celestium, which translates to On the Revolutions of the Celestial Spheres, and within its pages Copernicus had quietly rearranged the entire universe, moving the Earth from its ancient position at the center of all things and placing the Sun there instead, while our world became merely one of several planets circling that central fire in patient, yearly orbits. This was not an entirely new idea, for the ancient Greek philosopher Aristarchus had proposed something similar nearly 18 centuries earlier, but Copernicus developed the mathematics in careful detail, showing how such a system could explain the observed motions of the planets with reasonable accuracy, and in doing so he planted a seed that would slowly, over many generations, grow into our modern understanding of cosmic distances, though he could not have foreseen how troublesome and how ultimately liberating this rearrangement would prove to be. The Copernican system, as it came to be known, offered certain elegant simplifications in explaining why the planets sometimes appear to move backwards against the background stars, a phenomenon called retrograde motion, which had required rather complicated arrangements of circles upon circles in the older Earth-centered model inherited from the ancient astronomer Ptolemy. By placing the Sun at the center and allowing Earth to orbit around it, Copernicus showed that retrograde motion was simply an illusion created when Earth, moving faster in its smaller inner orbit, overtakes a slower outer planet, much as a car on a highway seems to make a slower vehicle appear to drift backwards when you pass it, though of course Copernicus had no highways to draw upon for such comparisons. Yet for all its conceptual appeal, the heliocentric model created a profound new problem for anyone who wished to measure the distances to the stars, a problem that would haunt astronomers for nearly 3 centuries and whose resolution would reveal a universe so vast that it still challenges the imagination to contemplate. The problem was this, and you may find it soothing to consider in the quiet of this moment. If Earth truly moves around the Sun in a great yearly circle, then the stars should appear to shift their position slightly when observed from opposite sides of that orbit, just as a nearby tree seems to move against the distant hills when you walk from one side of a field to the other. This apparent shifting of position due to viewing from different locations is called parallax, and it was a phenomenon well understood by astronomers of the 16th century, who used it routinely to measure distances to objects on Earth and had long sought to detect it in the heavens. In a heliocentric universe, the diameter of Earth's orbit would provide an enormous baseline for triangulation, and any astronomer patient enough to observe the same star 6 months apart, when Earth occupied opposite points in its journey around the Sun, should be able to detect some tiny displacement of that star against the more distant background. The fact that no one had ever observed such a displacement was, for many careful thinkers, a serious argument against the Copernican system, and nowhere was this argument pursued more rigorously than on a small island in the narrow strait between Denmark and Sweden. The island was called Ven, and the astronomer who made it famous was Tycho Brahe, a Danish nobleman with a silver nose, having lost part of his original nose in a duel in his youth, and a passion for precise observation that bordered on the obsessive. In 1576, the King of Denmark granted Tycho the entire island, along with generous funds to construct what would become the most sophisticated astronomical observatory the world had yet seen, a complex called Uraniborg after Urania, the muse of astronomy, followed later by a second underground observatory called Stjernborg when Tycho decided he needed even more stable conditions for his instruments. For over 20 years, from 1576 to 1597, Tycho and his assistants measured the positions of stars and planets with unprecedented accuracy, using enormous quadrants and sextants and armillary spheres, all crafted with painstaking care and calibrated with methods that Tycho himself devised. His observations were accurate to about 1 arcminute, which is to say 1/60th of a degree, and this was roughly 10 times better than anything achieved before, approaching the theoretical limit of what the human eye can accomplish without optical aid. And yet, despite all this precision, despite 2 decades of careful measurement, despite instruments that represented the finest technology of his age, Tycho Brahe could detect no parallax in any star. He searched and measured and compared observations taken months apart, and the stars remained stubbornly fixed in their positions, or at least any motion they displayed was smaller than his instruments could detect. For Tycho, this absence of observable parallax was decisive evidence against the Copernican system, for if Earth truly moved around the Sun, and if the stars were at any reasonable distance, then his instruments should have revealed the telltale shifting. The only way to reconcile a moving Earth with the absence of parallax was to assume that the stars were almost inconceivably far away, so far that even an orbit nearly 300 million kilometers in diameter produced an angular shift too small to measure, and this Tycho could not bring himself to accept. It seemed to him, and to many others, an absurdity, a violation of proportion, a cosmos designed with an inexplicable waste of space. And so Tycho developed his own compromise model of the universe, in which the Sun and Moon orbited Earth while all the other planets orbited the Sun, a system that preserved the mathematical advantages of Copernican theory while keeping Earth safely at rest and avoiding the troublesome implications of stellar parallax. It was an ingenious solution, and it satisfied Tycho's observational conscience, and it reminds us gently that the absence of evidence is not always evidence of absence, that sometimes the universe is simply larger than our instruments can reveal, and that the most careful observer, armed with the finest tools of their era, may still be looking through too narrow a window to perceive the truth. The failure to detect stellar parallax was not a failure of logic or method, but simply a limitation of technology, and the resolution of this limitation would require instruments that Tycho could not have imagined and patience measured in centuries rather than years. The early 17th century brought three developments that would slowly build the case for a heliocentric cosmos of vast dimensions, and we may consider each of them in turn with the unhurried attention they deserve. The first came from Johannes Kepler, a German mathematician who had worked as Tycho's assistant in the final years of that great observer's life and who inherited, after some legal complications, Tycho's precious treasury of planetary observations. Kepler was a man of mystical temperament but rigorous mathematical habits, and he spent years wrestling with the orbital data for Mars, seeking to find a geometric pattern that would match Tycho's careful measurements. After trying various arrangements of circles and epicycles without success, Kepler made the breakthrough that would reshape astronomy. He discovered that the orbits of planets are not circles but ellipses, with the Sun at one focus, and he formulated this and two other principles that we now call Kepler's laws of planetary motion. The first law describes the elliptical shape of orbits, the second explains how planets move faster when closer to the Sun and slower when farther away, and the third, published in 1619, establishes a precise mathematical relationship between a planet's orbital period and its average distance from a Sun. This third law is particularly significant for our quiet contemplation of cosmic distances, for it allowed astronomers to determine the relative distances of all the planets from the Sun, expressed not in any familiar unit like miles or kilometers, but in terms of the Earth's own distance from the Sun, a quantity that came to be called the astronomical unit. If you knew, for instance, that Jupiter takes approximately 12 years to orbit the Sun while Earth takes 1 year, then Kepler's third law told you that Jupiter must be approximately 5 times farther from the Sun than Earth is, though the actual value of that Earth-Sun distance, the astronomical unit itself, remained unknown. Kepler's laws thus provided a beautifully proportioned scale model of the solar system, like an architect's drawing with no indication of how large the finished building would be. The second development came in 1610, when Galileo Galilei pointed a newly invented device called a telescope at the night sky and beheld wonders that no human eye had ever perceived. He saw mountains on the moon, countless stars invisible to the naked eye, for small bodies orbiting Jupiter like a miniature planetary system, and, most relevant to our present discussion, the phases of Venus. Galileo observed that Venus displays a complete cycle of phases similar to our moon, waxing from crescent to full and back again, and that the apparent size of Venus changes dramatically throughout this cycle, appearing largest when in crescent phase and smallest when full. This pattern was precisely what the Copernican model predicted, for Venus would appear as a small full disk when on the far side of the Sun from us and as a large crescent when passing between Earth and Sun on its closer approach. The Earth-centered Ptolemaic model, by contrast, could not readily explain this observation, for in that system Venus should never show a full phase as seen from Earth. Galileo's telescope had thus provided strong visual evidence for the arrangement Copernicus had proposed, though it could not by itself reveal the actual scale of that arrangement. The third development, and perhaps the one most directly relevant to our gentle exploration of distance measurement, took place in 1672, when the French astronomer Giovanni Domenico Cassini organized an ambitious expedition to measure the distance to Mars using the method of parallax. The principle was straightforward, being the same triangulation method used by surveyors and mapmakers, but applied now to a celestial target. If two observers viewed Mars simultaneously from widely separated points on Earth, they would see it against slightly different background stars, and by measuring this difference and knowing the separation between the observers, the distance to Mars could be calculated. Cassini arranged for his colleague Jean Richer to travel to the town of Cayenne in French Guiana, near the equator in South America, while Cassini himself observed from the Paris Observatory. When Mars came to opposition in late 1672, meaning it was directly opposite the Sun as seen from Earth and therefore at its closest approach, both astronomers carefully measured its position against the background stars. The distance between Paris and Cayenne provided a baseline of several thousand kilometers, and the tiny difference in Mars's apparent position as seen from these two locations, combined with careful geometric calculations, yielded an estimate of the distance to Mars at that moment. From this measurement, using Kepler's laws to extend the result across the solar system, Cassini derived a value for the astronomical unit of approximately 140 million kilometers, which we may note is remarkably close to the modern accepted value of roughly 150 million kilometers. For the first time, humanity had a reasonably accurate measure of the scale of the solar system, not merely a relative model but an absolute determination in familiar units, and the number was sobering in its immensity. The Sun lay some 140 million kilometers from Earth, a distance so vast that a horse traveling at a steady trot would require thousands of years to cover it, though of course no horse was available for such a journey. And now we must pause to consider what this implied for the distant stars, those steadfast points of light that had refused to show any parallax despite Tycho Brahe's heroic efforts. If the distance from Earth to the Sun was 140 million kilometers, then the diameter of Earth's orbit was twice that, some 280 million kilometers, and this was the baseline that Tycho had effectively employed when searching for stellar parallax. His failure to detect any shift meant that even this enormous baseline was insufficient to produce a measurable angle, that the nearest stars must be not merely millions but hundreds of millions or even billions of times farther away than the Sun. The universe that emerged from these considerations was no longer the cozy medieval sphere with Earth at its center and the stars embedded in a crystalline shell just beyond Saturn, but an abyss of nearly incomprehensible depth, a darkness sprinkled with points of light separated by distances that defied ordinary imagination. This psychological transformation, from the intimate cosmos of Aristotle and Ptolemy to the vast emptiness of Copernicus and Kepler, occurred gradually over many generations, and it would be difficult to overstate its significance for human self-understanding. In the older model, Earth rested at the center of everything, motionless and special, surrounded by crystalline spheres carrying the Moon, the Sun, the planets, and finally the stars, with the realm of the divine just beyond the outermost sphere. It was a universe built to human scale, in some sense, a cosmic home with clear boundaries and a meaningful architecture. The new universe was almost exactly the opposite. Earth was a small planet orbiting an ordinary star, adrift in a void so immense that light itself, the fastest thing imaginable, would require years to cross even the shortest stellar distances, though this realization would come later, and the stars themselves were not fixtures in a nearby sphere but other suns scattered through an effectively infinite space. We cannot know with certainty how individual astronomers felt as this new picture came into focus, for they left behind measurements and calculations more often than confessions of cosmic vertigo, but we may imagine that some found it terrifying, others exhilarating, and many simply proceeded with their observations without pausing to contemplate the philosophical implications. The measurement of distance had begun as a practical matter, a question of how far away things might be, and had become, almost without anyone intending it, a complete reimagining of humanity's place in creation. The stars were far, impossibly far, and the techniques available in the 17th century could not yet reach them, could not pin down their distances with the same confidence that Cassini had achieved for Mars and the Sun. That achievement would require new instruments, new methods, and above all new patience, and the astronomers of subsequent centuries would rise to meet these challenges, one careful measurement at a time, as the story of cosmic distance continued to unfold in its gentle and unhurried way. In the early years of the 18th century, when astronomers had begun to understand the relative proportions of our solar system but still lacked any reliable measure of its true scale, a quiet realization began to take shape in the mind of Edmund Halley, the same careful observer who had calculated the orbit of the comet that would later bear his name. Halley understood that knowing the distance from Earth to the Sun was perhaps the most fundamental measurement one could hope to make, for upon this single value depended our understanding of everything beyond, the distances to the planets, the size of their orbits, and eventually, in centuries to come, the vast spaces between the stars themselves. And so, in 1716, Halley published a paper that would set in motion one of the most ambitious international scientific endeavors the world had yet seen, a paper that proposed using the rare passage of Venus across the face of the Sun to triangulate, through the geometry of parallax, just how far away our own star truly lies. The method Halley described was elegant in its conception, though demanding in its execution. When Venus passes directly between Earth and the Sun, an event that occurs in pairs separated by 8 years, with each pair more than a century apart, Observers stationed at different latitudes on Earth would see the tiny black disk of Venus trace slightly different paths across the solar face. By timing precisely when Venus appeared to touch the edge of the Sun at the beginning and end of its transit, and by comparing these timings between observers separated by thousands of miles, one could calculate the angle of parallax and thereby deduce the actual distance to the Sun in miles or kilometers, rather than merely knowing it as a ratio of other planetary distances. Halley himself would not live to see the transits he described, for the next pair would not occur until 1761 and 1769, but he wrote his paper as a message to future generations, urging them to prepare carefully and to station observers as widely across the globe as conditions would permit. When 1761 finally arrived, the astronomical community of Europe responded to Halley's call with remarkable coordination, despite the considerable complication that much of Europe was then embroiled in the 7 Years' War, a sprawling conflict that touched 4 continents and set traditional allies against one another in unfamiliar configurations. Nevertheless, more than 120 observers spread themselves across the globe, from Siberia to the southern tip of Africa, from the frozen reaches of Scandinavia to the tropical islands of the Indian Ocean. This was scientific cooperation on a scale never before attempted, and it required not only astronomical expertise but considerable courage and physical endurance, for many of these observers would spend years away from home, traveling to remote locations by ship and by horse, carrying delicate instruments across landscapes that offered neither comfort nor certainty of safe return. Among the observers of the 1761 transit was Mikhail Lomonosov, the Russian polymath who watched from St. Petersburg and who, in doing so, made an unexpected discovery that had nothing to do with the distance to the Sun. As Venus began its slow crawl onto the solar disk, Lomonosov noticed a thin luminous arc appearing around the portion of the planet that still lay against the darkness of space, a subtle halo of light that could only be explained if Venus possessed an atmosphere of its own, an envelope of gases capable of refracting and scattering sunlight around the planetary limb. This observation, made almost incidentally while pursuing the primary goal of timing the transit, revealed that other worlds might possess atmospheres not entirely unlike our own, a gentle revelation that expanded the imagination of what planets might be. From the Cape of Good Hope, at the southern tip of Africa, 2 Englishmen named Charles Mason and Jeremiah Dixon carried out their own careful observations. These 2 men would later become famous for surveying the boundary line between Pennsylvania and Maryland that still bears their names, but in 1761 they were simply dedicated astronomers who had accepted the Royal Society's request to travel far from home in pursuit of accurate transit timings. Their journey had not been without incident, for their ship had been attacked by a French frigate before they even left the English Channel, a reminder that the war made no exceptions for scientific missions. But they persevered, repaired their vessel, and eventually reached the Cape, where they set up their instruments and watched as Venus made its slow journey across the Sun, adding their measurements to the growing collection that astronomers hoped would yield the answer Halley had sought. But perhaps no story from the 1761 transit is more quietly heartbreaking than that of Guillaume Le Gentil, a French astronomer whose dedication to science would cost him nearly everything. Le Gentil set out from France in 1760, his destination the French colony of Pondicherry on the southeastern coast of India, a location chosen for its favorable latitude and its reasonably clear skies. He sailed for months, carrying his telescopes and timing instruments across the Atlantic and around the Cape of Good Hope, only to learn, as his ship approached the Indian coast, that Pondicherry had fallen to British forces. The war had reached his destination before he had, and there was no safe place for him to land and set up his equipment. On the day of the transit itself, the 6th of June, 1761, Le Gentil found himself still at sea, the rolling deck of his ship making precise observations impossible, the clouds that drifted across the sky adding further insult to his already untenable situation. He watched Venus cross the Sun, but he could take no useful measurements, and so his years of preparation came to nothing. A lesser man might have returned home in defeat, but Le Gentil made a decision that speaks to both his scientific commitment and perhaps a certain stubbornness of character. He would stay in the region and wait for the next transit, 8 years hence, in 1769. He spent the intervening years exploring Madagascar, mapping the coastlines of the Indian Ocean, studying the natural history of the islands he visited, and eventually making his way back to Pondicherry, which had by then been returned to French control. He built a small observatory, tested his instruments repeatedly, and waited with the patience of a man who had already sacrificed so much and could not bear to sacrifice more. When the day of the 1769 transit finally arrived, Le Gentil was ready, his equipment calibrated, his methods rehearsed, his hopes surely tempered by experience but not extinguished entirely. And then the clouds came. After weeks of clear skies, the morning of the transit dawned overcast, and Le Gentil could see nothing at all. He had waited 8 years, travelled tens of thousands of miles, and the weather had betrayed him at the final moment. The accounts suggest that this blow affected him deeply, that he fell into a prolonged illness from which he slowly recovered. When he finally returned to France, after more than 11 years away, he discovered that he had been declared legally dead, his estate had been divided among his heirs, his seat in the Royal Academy of Sciences had been given to another, and his wife had remarried. He spent years in legal proceedings to reclaim what had been his, and though he eventually succeeded in restoring some portion of his former life, the cost of chasing Venus had been higher than any astronomer should have to pay. The 1769 transit brought fresh expeditions and fresh tragedies of its own. The British Admiralty, recognizing the scientific importance of the occasion, commissioned a voyage to the southern Pacific Ocean, where observers might watch the transit from latitudes unavailable elsewhere on Earth. Command of this expedition was given to a naval lieutenant named James Cook, a skilled navigator and cartographer who would later become famous for his explorations of the Pacific, but who in 1769 was simply the capable officer entrusted with delivering a team of astronomers to the island of Tahiti. Cook's vessel was the Endeavour, a sturdy bark originally built for carrying coal, chosen for its reliability rather than its speed, and the astronomers aboard included Charles Green, who had served as assistant to the Astronomer Royal, and the wealthy naturalist Joseph Banks, who had his own scientific interests to pursue. The Endeavour reached Tahiti in April of 1769, and Cook established an observation point on the northern shore of the island, a location that would come to be known as Point Venus in honor of the transit it was built to observe. The local Tahitians were curious about these visitors and their strange instruments, and relations between the two groups were generally cordial, though not without the occasional misunderstanding. When the transit came, on the 3rd of June, the skies were clear, and the observers watched as the small black circle of Venus crept onto the bright disk of the Sun and began its slow traverse. But here the observers encountered a phenomenon that would plague transit measurements for centuries, an optical effect known as the black drop. At the moment when Venus should have appeared to touch the inner edge of the Sun, a dark ligament seemed to connect the planet to the solar limb, making it impossible to determine the precise instant of contact. The effect was subtle but maddening, introducing uncertainties of many seconds into measurements that needed to be accurate to fractions of a second. Different observers, watching through different telescopes, recorded slightly different times for the same event, and the hoped-for precision proved elusive. The black drop effect arises from a combination of factors, including the blurring caused by Earth's atmosphere, the optical properties of the telescopes themselves, and the inherent difficulty of judging when two dark areas truly merge into one. It was a reminder that nature does not always cooperate with our desire for clean measurements. Nevertheless, the 1769 observations were sufficient to allow astronomers to calculate a reasonably accurate value for the solar distance. Thomas Hornsby, the civilian professor of astronomy at Oxford, compiled and analyzed the observations from around the world and concluded that the Sun lay approximately 93 million miles from Earth, a value that subsequent measurements have refined only slightly. This number, the astronomical unit, became the foundation upon which all further cosmic distance measurements would be built, the first rung of what astronomers would later call the cosmic distance ladder, a series of interlocking methods that would eventually carry human understanding out to the farthest reaches of the observable universe. Among those who did not return from the 1769 transit expeditions was Jean-Baptiste Chappe-Diodroche, a French astronomer who had successfully observed the 1761 transit from Tobolsk in Siberia, enduring a grueling winter journey across Russia to reach his station in time. For 1769, Chappe traveled to Baja California, then a remote and sparsely settled peninsula on the western edge of New Spain. He reached his destination, set up his instruments, and observed the transit successfully, obtaining high-quality measurements that would contribute to Hornsby's calculations. But an epidemic of typhus was sweeping through the region, and Chappe, along with most of his party, fell ill. He died just weeks after his successful observation, his notes and data carried back to Europe by the few survivors of his expedition. His sacrifice was quieter than Legental's long suffering, but no less real, a life given to the pursuit of a single measurement. The transit of Venus expeditions of 1761 and 1769 represented something new in the history of science, a coordinated international effort that transcended the boundaries of war and national rivalry, at least for a time. Astronomers from France and Britain, from Russia and the American colonies, from Sweden and Austria and the German states, all contributed their observations to a common goal, pooling data across borders in a manner that prefigured the international scientific collaborations of later centuries. The distance to the Sun was not the discovery of any single nation, but a collective achievement of careful observation and patient calculation, a testament to what could be accomplished when curiosity was allowed to override conflict, at least within the quiet community of those who watched the skies. And so we come now to the moment when the stars, at last, gave up their secret distances, when centuries of patient effort and refined instruments and careful thought finally converged upon a measurement that had eluded the greatest minds in astronomy, and we find ourselves in the quiet observatories of northern Europe in the 1830s, where astronomers work through long winter nights, their eyes pressed to instruments of extraordinary precision, seeking an angular shift so small that it had defeated every previous attempt to detect it, and we shall see how three men, working independently in different corners of the world, each found their way to the same profound truth, that the stars are incomprehensibly far away, far more distant than most had dared to imagine, and that the universe we inhabit extends outward to distances measured not in thousands or millions of miles, but in trillions upon trillions, a revelation both humbling and strangely comforting in its grandeur. The principle of stellar parallax, as we have discussed in earlier portions of our story, is beautifully simple in its conception, for it relies upon nothing more exotic than the geometry of triangles, the same mathematics that surveyors use when measuring the width of rivers or the height of mountains, applied now to the vast gulfs between ourselves and the stars. And the method asks only that we observe a star from two different positions in space, positions separated by a known distance, and measure how much the star appears to shift against the background of more distant stars, just as your thumb seems to jump back and forth when you view it first with one eye and then with the other, and the Earth itself provides the baseline for this measurement, for as our planet swings around the Sun in its yearly orbit, we find ourselves in January some 300 million kilometers from where we stood in July, and this cosmic baseline, the diameter of Earth's orbit, ought in principle to produce a detectable shift in the apparent positions of nearby stars, assuming those stars are close enough for the geometry to work, and assuming our instruments are sensitive enough to detect the tiny angular displacements involved. But the detection of this shift proved extraordinarily difficult, so difficult that for more than 2,000 years astronomers had searched for it without success, and the absence of observable parallax had been used by those who opposed the Copernican model as evidence that the Earth must be stationary, for if we truly orbited the Sun, they argued, we should see the stars wobbling back and forth as we moved. And the only defense available to Copernicus and his followers was to suggest that the stars must be enormously far away, so distant that even our orbital motion produced no measurable effect, and this explanation, while correct, seemed to many an unsatisfying evasion, a hypothesis designed to rescue a theory rather than a conclusion drawn from observation. And so the search for stellar parallax became one of the great quests of astronomy, a prize sought by generation after generation of observers, each convinced that better instruments and more careful techniques would finally reveal what nature had thus far concealed. The English astronomer James Bradley provides us with a poignant example of how this search could lead to unexpected discoveries, for in 1727, while carefully monitoring the positions of stars in hopes of detecting parallax, Bradley noticed that the stars did indeed appear to shift their positions over the course of a year, but not in the pattern that parallax would produce, and after much puzzlement and careful analysis, he realized that what he was observing was something quite different, a phenomenon we now call stellar aberration, which arises from the combination of the Earth's orbital velocity and the finite speed of light, rather like the way raindrops falling straight down appear to slant toward you when you run through them. And this discovery was itself of great importance, providing independent confirmation that the Earth truly moves through space, and Bradley continued his observations for many more years, eventually discovering yet another phenomenon. The slow nodding motion of Earth's axis known as nutation, caused by gravitational influences of the Moon, but the parallax he sought continued to elude him, for his instruments, excellent though they were for their time, could not achieve the precision necessary to detect the tiny angular shifts involved, shifts that we now know to be far smaller than anything the technology of his era could measure. To understand just how challenging this measurement was, it helps to consider the scale of the angular displacements involved, for when astronomers speak of stellar parallax, they measure it in arcseconds, which are tiny subdivisions of a degree, with each degree of arc divided into 60 arc-minutes and each arc-minute further divided into 60 arc-seconds, so that one arc-second represents 1/3600th of a degree. And to give you some sense of how small this is, imagine looking at a small coin, perhaps a 5-cent piece, and then imagine carrying that coin away from you until it sat at a distance of 100 miles, and the angle subtended by that distant coin would be roughly 1 arc-second, and the stellar parallaxes that Bessel and his contemporaries were attempting to detect were even smaller than this, fractions of an arc-second. Angular shifts so minute that they pushed the very limits of what the human eye could perceive even with the finest instruments, and they atmospheric trembling that makes stars twinkle, along with tiny flexures in telescope tubes and imperfections in optical components, all conspired to mask these delicate signals beneath layers of noise and systematic error. The breakthrough came through a combination of improved instruments, carefully chosen targets, and observers of exceptional patience and skill, and the astronomers who succeeded in this quest had learned from the failures of their predecessors that the key lay not in building ever larger telescopes, for size alone would not help, but in constructing instruments capable of measuring angular positions with extraordinary precision. And one such instrument was the heliometer, originally designed for measuring the diameter of the Sun, which used a split lens to produce two images of a star that could be brought together or separated by turning a finely threaded screw, allowing the observer to measure angular separations with a precision previously unattainable. And it was with such an instrument, built by the renowned optician Joseph von Fraunhofer, that Friedrich Wilhelm Bessel set out to accomplish what so many had attempted and failed. Bessel worked at the Königsberg Observatory in what was then East Prussia, now part of Russia, and he brought to the task not only fine instruments but also a rigorous mathematical approach to the analysis of observations, for he understood that systematic errors could mimic or mask the tiny signal he sought, and that only through careful statistical treatment of many observations could the truth be extracted from a noise. And he chose as his target a star known as 61 Cygni, in the constellation of the Swan, a star that was not particularly bright, being only faintly visible to the unaided eye, but which possessed a characteristic that made it especially promising for parallax work, namely a large proper motion, which is to say that 61 Cygni appeared to drift across the sky relative to the background stars at a rate faster than almost any other star then known. And this rapid proper motion suggested that the star might be relatively close to us, for just as nearby objects appear to move faster when viewed from a moving train, so too might nearby stars appear to drift more quickly across the celestial sphere as our solar system travels through the galaxy. And Bessel reasoned that a nearby star would exhibit a larger parallax and thus be easier to detect. Over the course of more than a year, from 1837 into 1838, Bessel made hundreds of careful observations of 61 Cygni, comparing its position to that of fainter background stars that he assumed to be much more distant, and slowly, methodically, the data began to reveal a pattern, a tiny back-and-forth wobble that corresponded precisely to the predictions of parallax theory, with the star appearing to shift in one direction during one part of the year and in the opposite direction 6 months later. And when Bessel announced his results in 1838, he reported a parallax of approximately 0.314 arc-seconds, which corresponded to a distance of about 10.3 light-years, meaning that the light we see from 61 Cygni tonight left that star more than a decade ago and has been traveling through the void of space ever since, and this distance, expressed in more conventional units, amounts to roughly 60 trillion miles, a number so large that it challenges our ability to comprehend it. And yet 61 Cygni is one of our very nearest stellar neighbors, a cosmic next-door acquaintance in the vastness of the galaxy. But Bessel was not the only astronomer to achieve this long-sought goal in those remarkable years, for Thomas Henderson, a Scottish astronomer working at the Royal Observatory at the Cape of Good Hope in South Africa, had actually obtained the necessary observations even earlier, during 1832 and 1833, though he did not publish his results until 1839, some months after Bessel's announcement, and Henderson had chosen a different target, the bright star Alpha Centauri, which dominates the southern skies and which also displayed a high proper motion suggestive of proximity, and his measurements revealed a parallax of approximately 0.75 arcseconds, substantially larger than that of 61 Cygni, indicating that Alpha Centauri was substantially closer, at a distance we now know to be about 4.3 light-years, making it the nearest star to our Sun, or rather the nearest star system, for Alpha Centauri is in fact a triple star, with two Sun-like stars orbiting each other closely and a third, fainter companion known as Proxima Centauri, which is actually the closest of the three to us, though this was not known until much later. Henderson's delay in publishing has sometimes been attributed to doubts about his own measurements, for he worried that such a large parallax might indicate an error rather than a genuine detection, and the psychological pressure of making such a momentous claim may have given him pause, or perhaps he simply lacked the confident mathematical framework that Bessel had developed for extracting reliable results from noisy data. But regardless of the reason, the delay meant that Bessel received the priority for the first published stellar parallax, though history properly acknowledges both men, along with a third, Friedrich Georg Wilhelm Struve, who working at the Dorpat Observatory in what is now Estonia used yet another fine Fraunhofer instrument to measure the parallax of Vega, the brilliant blue-white star that marks the apex of the summer triangle, announcing his preliminary results in 1837, and while Struve's measurement proved somewhat less accurate than the others, his independent confirmation added weight to the overall conclusion that stellar parallaxes had at last been detected. The psychological impact of these measurements upon the astronomical community and upon educated society more broadly cannot be overstated, for here at last was direct, geometric proof that the stars were other suns, scattered through a universe of staggering immensity, and the Copernican model, which had remained somewhat controversial in certain quarters for 3 centuries, was now vindicated beyond reasonable doubt, for the Earth truly did orbit the Sun, and the parallactic shift that such an orbit must produce had finally been observed, and the apparent absence of parallax in earlier observations was explained not by a stationary Earth but by the tremendous distances to even the nearest stars, distances so great that the entire orbit of the Earth, 300 million kilometers wide, shrinks to a mere pinpoint from the perspective of the stars, and we find ourselves confirmed as inhabitants of a small world circling an ordinary star in a universe vast beyond comprehension. And there is something deeply comforting in this knowledge, in understanding our place in the cosmic order, even if that place is humble by some measures, for we are part of something magnificent and ancient and unimaginably large. And yet we must acknowledge the limitations of the parallax method, for it works only for relatively nearby stars, those within perhaps 100 light-years of the Sun, and even at those distances the parallax angles become so small, mere hundredths or thousandths of an arcsecond, that ground-based measurements struggle to detect them reliably, and the overwhelming majority of stars in our galaxy, which contains hundreds of billions of stars spread across a disk 100,000 light-years in diameter, lie far beyond the reach of parallax measurements, and so while Bessel and Henderson and Struve had taken an essential first step, calibrating the cosmic distance ladder at its very first rung, much work remained to be done, and other methods, building upon the foundation of parallax, would be needed to probe ever deeper into the universe, and we shall explore those methods in their turn. But for now we may rest content in knowing that the stars of distances, that those distances can be measured, and that patient observation combined with careful thought can reveal truths that once seemed forever beyond our grasp, and the light of 61 Cygni continues to fall upon the Earth tonight just as it did when Bessel watched it through his heliometer. And in some quiet sense we are connected to those distant suns by the very photons that cross the void to reach our eyes. In the early years of the 20th century, in a brick building on the grounds of Harvard College Observatory, a a woman sat at a wooden desk examining glass photographic plates, each one a captured image of the southern sky. Her name was Henrietta Swan Leavitt, and she was employed as what the observatory called a computer, which in those days meant not a machine but a person, usually a woman, who performed the painstaking calculations and measurements that the male astronomers required for their research. For this meticulous work, she earned 25 cents per hour, a wage that reflected both the era's general undervaluation of such labor and its particular undervaluation of women's contributions to science. She worked in a large room alongside other women computers, all of them bent over magnifying glasses and logarithm tables, cataloging the brightness of stars one by one, recording their observations in neat handwritten columns that would eventually fill volumes of published catalogues. The work was repetitive in the way that important scientific work often is, requiring not flashes of inspiration so much as sustained attention, careful comparison, and an almost meditative willingness to notice small patterns emerging from vast quantities of data. Henrietta Leavitt had come to this work somewhat circuitously, having studied at what was then called the Society for the Collegiate Instruction of Women, later known as Radcliffe College, where she had taken a course in astronomy during her final year and discovered an aptitude for the careful observation of celestial phenomena. After graduating, she had traveled and then become seriously ill, an illness that left her progressively deaf for the rest of her life, though this did not prevent her from continuing her work, since the examination of photographic plates required keen eyesight rather than hearing. She had joined the observatory in 1893 as a volunteer, which was one of the few ways women could gain access to astronomical research at that time, and she was eventually hired as a permanent staff member, though always at the modest wage that was deemed appropriate for women's work. The director of the observatory was Edward Pickering, who had pioneered the hiring of women computers, recognizing that they could perform the detailed work of stellar classification with accuracy and at considerably lower cost than male astronomers would demand. His team of women computers became known, somewhat dismissively, as Pickering's harem, though several of them would go on to make contributions of lasting importance to astronomy, and Henrietta Leavitt's contribution would prove to be among the most consequential of all. The photographic plates she studied had been taken at a station in Peru, where Harvard maintained a telescope for observing the southern skies that were not visible from Massachusetts. Among the objects captured on these plates was the Small Magellanic Cloud, a fuzzy patch of light visible from the southern hemisphere that we now know to be a small galaxy orbiting our own Milky Way, though in Leavitt's time its true nature was still uncertain. What was clear from the photographs was that the Small Magellanic Cloud contained many stars, and Leavitt had been assigned the task of identifying variable stars within it, stars whose brightness changed over time in regular or irregular patterns. To find these variable stars, she had to compare multiple photographs of the same region of sky taken on different nights, looking for stars that appeared brighter in some images and dimmer in others. This required laying one plate over another and examining them through a magnifying glass, noting any discrepancies, then measuring the brightness of suspect stars using a device that compared them to reference stars of known magnitude. It was slow work, a single plate sometimes taking many hours to examine thoroughly, and the Small Magellanic Cloud contained thousands upon thousands of stars crowded together in the photographs. By 1908, Henrietta Leavitt had identified 1,777 variable stars in the Small Magellanic Cloud, an impressive number that represented years of careful observation. But more important than the quantity of her discoveries was the pattern she began to notice among a particular type of variable star, the Cepheid variables. These stars are named after Delta Cephei, the first of their type to be identified, and they are characterized by a very regular pattern of brightening and dimming, like a slow cosmic heartbeat. Unlike some variable stars whose changes are erratic or unpredictable, Cepheids pulse with clockwork regularity, their brightness rising and falling over periods ranging from a few days to several weeks. What Leavitt noticed, as she tabulated the periods and brightness of more and more Cepheids in the Small Magellanic Cloud, was that the brighter ones seemed to have longer periods. A Cepheid that took a month to complete its cycle of brightening and dimming was, on average, noticeably brighter than one that completed the same cycle in only a few days. This might seem like a minor observation, a curious correlation of the sort that appears in many datasets without necessarily meaning anything profound. But Leavitt recognized that this particular correlation had remarkable implications because of a simple but crucial fact about the Small Magellanic Cloud. Because the Small Magellanic Cloud is very far away from us, and because it is relatively small compared to that vast distance, all the stars within it are approximately the same distance from Earth. It is rather like looking at a distant city from many miles away, where all the buildings appear roughly the same distance from you, even though some are at the near edge of the city and others at the far edge, because the city itself is small compared to how far away it is. This meant that when Leavitt observed one Cepheid in the Small Magellanic Cloud to be brighter than another, the difference in apparent brightness reflected a genuine difference in actual luminosity. The brighter star was not merely closer, it was truly putting out more light. And if brighter Cepheids truly were more luminous, and if brighter Cepheids had longer periods, then there was a direct relationship between a Cepheid's pulsation period, something that could be measured from anywhere, and its intrinsic luminosity, its true power output. In 1912, Henrietta Leavitt published her findings in the Harvard College Observatory Circular, presenting what we now call the period-luminosity relationship for Cepheid variable stars. The publication appeared under Edward Pickering's name, as was common practice at the time, with Leavitt credited only as having prepared the data, though the insight was entirely hers. The relationship she had discovered was clear and consistent. The longer a Cepheid's period, the greater its intrinsic brightness, with the relationship following a smooth curve that could be expressed mathematically. A Cepheid with a period of 10 days was roughly twice as luminous as one with a period of 3 days, and one with a period of 30 days was brighter still, following a predictable pattern. The significance of this discovery for measuring cosmic distances is profound and worth lingering over for a moment. If you know how bright a star truly is, its intrinsic luminosity, and you can measure how bright it appears to be from Earth, its apparent brightness, then you can calculate how far away it must be. This is because light spreads out as it travels through space, becoming dimmer with distance according to a precise mathematical law, the inverse square law, which says that doubling the distance reduces apparent brightness to 1/4, tripling the distance reduces it to 1/9, and so on. Before Leavitt's discovery, astronomers had no way of knowing the intrinsic luminosity of distant stars. They could measure how bright stars appeared but had no way of knowing whether a dim star was truly faint or simply very far away. Leavitt's period-luminosity relationship changed this, because now an astronomer who observed a Cepheid variable anywhere in the sky could measure its period, a straightforward task requiring only patience and repeated observation, and from that period could deduce the star's true luminosity, and from the difference between that true luminosity and the star's apparent brightness could calculate its distance. The Cepheid variables had become what astronomers would call a standard candle, a type of object whose intrinsic brightness is known, and which can therefore serve as a cosmic yardstick for measuring distances far beyond the reach of parallax. But there was still a crucial piece missing from the puzzle. Leavitt's relationship told astronomers that brighter Cepheids had longer periods, but it did not tell them in absolute terms exactly how bright a Cepheid of any given period actually was. To use Cepheids as distance indicators, someone needed to calibrate the relationship, to determine the actual luminosity of at least one Cepheid at a known distance, which could then serve as a reference point for all the others. This calibration was accomplished in 1913 by the Danish astronomer Ejnar Hertzsprung, who used a technique called statistical parallax to estimate the distances to a number of Cepheids in our own galaxy. Statistical parallax is a clever method that combines the proper motions of many stars, their apparent movement across the sky due to their actual motion through space, with assumptions about the average behavior of stellar motions to derive statistical estimates of distance. It is less precise than geometric parallax but can reach somewhat further into space, and Hertzsprung used it to establish approximate distances to enough Cepheids that he could determine where the period-luminosity relationship fell in absolute terms. With this calibration in hand, astronomers could now take any Cepheid anywhere in the sky, measure its period, look up its intrinsic luminosity from Leavitt's relationship as calibrated by Hertzsprung, compare that to its apparent brightness, and calculate its distance. The American astronomer Harlow Shapley was among the first to put this new tool to dramatic use. In 1918, Shapley used Cepheid variables to measure the distances to globular clusters, those dense spherical swarms of ancient stars that orbit around the center of our galaxy. By identifying Cepheids within these clusters and measuring their periods, he could determine how far away each cluster lay. The results were startling. The globular clusters were far more distant than anyone had supposed, spread across a vast volume of space that implied the Milky Way itself was much larger than previous estimates had suggested, perhaps 100,000 light-years across. Even more significantly, Shapley noticed that the globular clusters were not distributed evenly around the sky but were concentrated in one direction, toward the constellation Sagittarius. From this, he concluded that our Sun was not at the center of the galaxy, as had long been assumed, but rather off to one side, orbiting the true galactic center along with all the other stars in our stellar neighborhood. This was a displacement of human significance comparable in some ways to the Copernican displacement of Earth from the center of the solar system, though it attracted rather less controversy. All of this, the measurement of stellar distances on scales of tens of thousands of light-years, the mapping of our galaxy's true size and shape, the displacement of the Sun from any position of cosmic centrality, flowed from the careful observations of a woman earning 25 cents an hour examining photographic plates in Cambridge, Massachusetts. Henrietta Leavitt did not live to see the full flowering of her discovery. She died in December of 1921 from cancer, at the age of 53, still working at the observatory in the relatively modest position she had always held. A few years after her death, a member of the Swedish Academy of Sciences wrote to Harlow Shapley to inquire about nominating Leavitt for the Nobel Prize in Physics, not knowing that she had already died and that Nobel Prizes are not awarded posthumously. It is impossible to say whether she would have received the prize had she lived longer, but many historians of science believe her discovery was worthy of that recognition, and that the oversight reflects both the general undervaluation of women's scientific work in that era and the particular invisibility of the patient, methodical labor that often underlies great discoveries. What Leavitt could not have known, though perhaps she might have sensed, was that her period luminosity relationship would soon carry astronomers far beyond the Milky Way itself, into distances measured not in thousands but in millions of light-years. In the years following her death, Edwin Hubble would use Cepheid variables to demonstrate that certain fuzzy patches of light long thought to be nebulae within our own galaxy were in fact separate galaxies in their own right, island universes lying at almost inconceivable distances across the void. The key that unlocked the true scale of the cosmos, the standard candle that illuminated the darkness between galaxies, was the relationship that Henrietta Swan Leavitt had patiently extracted from 1,700 photographic measurements of stars in a cloud visible only from the southern hemisphere, working at a desk in a brick building, counting periods and magnitudes, noticing that brighter Cepheids pulsed more slowly, and recognizing that this simple pattern was a gift of immense value to anyone who wished to know how far away the stars might be. In the early decades of the 20th century, astronomers found themselves confronting a question of almost unimaginable scope, a question that concerned nothing less than the size and structure of everything that exists, and yet for all its grandeur this question hinged upon the interpretation of faint smudges of light that could be seen through telescopes, pale spiral forms that drifted among the stars like wisps of luminous cloud, and the nature of these spiral nebulae, as they were called, would become the subject of one of the most consequential disagreements in the history of astronomy, a gentle but profound contest of ideas that would ultimately reshape humanity's understanding of its place in the cosmos. The prevailing view at the time held that our Milky Way galaxy represented the entirety of the universe, a vast but finite system of stars surrounded by empty darkness, and within this framework the spiral nebulae were understood to be relatively nearby objects, perhaps clouds of glowing gas or regions where new solar systems were forming, curious features within our galactic home but nothing more remarkable than that, and this interpretation seemed sensible enough given the tools and knowledge available, for the nebulae appeared small and their distances could not be measured directly, leaving astronomers to speculate based upon their apparent size and brightness. But there existed an alternative possibility, one that had been suggested as early as the 18th century by philosophers and astronomers who gazed upon these spiral forms and wondered whether they might be something far grander than mere clouds, whether in fact each spiral nebula might be an entire system of stars comparable to our own Milky Way, separated from us by unthinkable gulfs of empty space, And if this were true, then the universe would be not one galaxy but countless galaxies, each an island of stars floating in an ocean of darkness so vast that light itself would require millions of years to cross from one island to the next. And this notion of island universes, as they came to be called, carried implications so profound that many astronomers found it difficult to accept. On the 26th of April in the year 1920, a formal discussion was arranged at the Smithsonian Institution in Washington to address this very question, bringing together two distinguished astronomers whose views on the nature of the spiral nebulae stood in direct opposition, and this gathering would later come to be known as the Great Debate, though at the time it was simply a scholarly exchange of perspectives, conducted with the measured civility that characterizes academic discourse, each participant presenting his evidence and his reasoning while the other listened and prepared his response, the audience sitting quietly in their chairs as the fate of the universe hung in the balance of careful argumentation. Harlow Shapley, a young astronomer of considerable accomplishment who had recently completed groundbreaking work on the size and structure of the Milky Way, argued forcefully that our galaxy encompassed the entire universe, that the spiral nebulae were relatively small and relatively nearby objects contained within or just beyond the boundaries of our stellar system. And his position was not mere stubbornness or failure of imagination, but was grounded in what he believed to be solid observational evidence, for Shapley had measured the distribution of globular star clusters surrounding the Milky Way and had concluded that our galaxy was far larger than previously supposed, spanning perhaps 300,000 light-years from edge to edge, a dimension so enormous that it seemed to leave little room for additional galaxies beyond. Heber Curtis, an older and more cautious astronomer who had spent years studying the spiral nebulae through the telescopes at Lick Observatory in California, presented the opposing view, arguing that these spiral forms were indeed distant island universes, each one a galaxy unto itself containing billions upon billions of stars. And Curtis supported his position by pointing to certain features of the spirals that suggested they were similar to our own Milky Way, including the presence of dark lanes that might be bands of obscuring dust, and the occasional appearance of novae within the spirals, sudden brightenings that resembled the stellar explosions observed in our own galaxy, though if these novae were truly comparable to those in the Milky Way, then the spirals must be at distances measured in millions of light-years, placing them far beyond the boundaries of any single galactic system. The debate that evening did not produce a clear victor, for both participants presented compelling arguments and neither could offer definitive proof, and the astronomers in attendance went home that night with the question still unresolved, each perhaps favoring one position or the other based upon temperament and interpretation, but none able to claim certain knowledge, and this uncertainty would persist for several more years, the nature of the spiral nebulae remaining one of the great open questions of astronomy, a puzzle that awaited the development of more powerful instruments and more precise methods of measurement. Among the evidence that seemed to support Shapley's position were certain measurements made by Adrian van Maanen, a respected astronomer at the Mount Wilson Observatory in California who had undertaken a painstaking study of several spiral nebulae, comparing photographic plates taken years apart in an attempt to detect any rotation of these structures, any slow turning of their spiral arms that might reveal something about their nature and distance, and van Maanen reported that he had indeed detected such rotation, measuring angular movements that, if real, would imply that the spirals must be relatively nearby, for if they were truly at the immense distances required by the island universe hypothesis, then their rotation would be imperceptibly slow, their spiral arms taking hundreds of millions of years to complete a single turn, far too gradual to detect over the span of a human lifetime. These measurements by van Maanen were careful and methodical, conducted according to the best practices of the time, and they seem to provide strong support for the notion that spiral nebulae were small and close, mere appendages of our own galactic system rather than independent universes in their own right, and for several years these results influenced the thinking of many astronomers, including Shapley himself, who cited van Maanen's work as evidence for his position, though, as it would later emerge, these measurements were in error, not through any dishonesty or carelessness on van Maanen's part, but through some systematic bias in his method that has never been fully explained, the human eye and hand conspiring somehow to produce results that were entirely spurious, a sobering reminder of how even the most dedicated scientist may be led astray by the limitations of perception. The resolution of the great debate would come not from further argument but from a single, quiet observation made on a clear autumn night at the Mount Wilson Observatory, high in the mountains above Los Angeles where the air is thin and steady and the great dome of the 100-inch Hooker telescope stands silhouetted against the stars. And it was here, on the evening of the 5th and 6th of October in 1923, that Edwin Hubble, a tall and deliberate man who had come to astronomy after studying law and serving in the Great War, trained the most powerful telescope in the world upon the Great Spiral Nebula in the constellation Andromeda and captured upon a glass photographic plate an image that would change everything. Hubble was searching for novae, those sudden stellar explosions that occasionally flare up in the Andromeda Nebula and then fade away. And upon examining his photographic plate he found what appeared to be a nova in one of the outer regions of the spiral, marking its position on the plate with the letter N to indicate its nature, a small notation in ink that seemed ordinary enough at the time. One more observation among thousands in the meticulous records of the observatory, and yet this particular point of light would prove to be something far more significant than a simple nova, something that would provide at last the means to measure the distance to the spiral nebulae and resolve the question that had so long divided astronomers. For when Hubble compared his new photograph with older plates of the same region, taken months and years earlier, he discovered that this star had not simply flared up and faded as a nova would, but had instead brightened and dimmed in a regular, repeating pattern, growing luminous and then faint and then luminous again over a period of approximately 31 days. And this behavior was characteristic not of a nova but of a Cepheid variable star, one of those remarkable stellar beacons whose brightness waxes and wanes like a slow celestial heartbeat, and Hubble, recognizing what he had found, crossed out the letter N on his photographic plate and wrote beside it the letters VAR followed by an exclamation mark, a small gesture of excitement that is preserved to this day in the observatory archives, the only punctuation mark in this entire story. The significance of finding a Cepheid variable in the Andromeda Nebula cannot be overstated, for thanks to the pioneering work of Henrietta Leavitt more than a decade earlier the relationship between the pulsation period of a Cepheid and its intrinsic luminosity was well established, meaning that by measuring how long this star took to complete one cycle of brightening and dimming Hubble could determine how luminous it truly was, and by comparing this true luminosity with how faint the star appeared in his telescope he could calculate how far away it must be, the same method of standard candles that had proven so successful in mapping the structure of our own galaxy, now applied for the first time to an object whose nature had been so long in dispute. Hubble performed the calculations carefully, checking and rechecking his figures, measuring the period of the variable star with precision and applying the period luminosity relation to determine its absolute brightness, and when at last he converted apparent magnitude to distance he arrived at a number that was staggering in its implications, a distance of approximately 900,000 light-years, placing the Andromeda Nebula far beyond the outermost boundaries of the Milky Way, far beyond any distance that could be reconciled with the notion that spiral nebulae were merely nearby clouds of gas, and though this estimate would later be revised upward as astronomers discovered that there were two types of Cepheid variables with different period luminosity relations, eventually settling upon a distance of approximately 2.5 million light-years, even Hubble's initial measurement was sufficient to settle the debate, to demonstrate beyond reasonable doubt that the spiral nebulae were indeed island universes, galaxies unto themselves, scattered across a cosmos of almost incomprehensible vastness. In February of 1924, Hubble composed a letter to Harlow Shapley informing him of the discovery, a brief and factual communication conveying the news that a Cepheid variable had been found in Andromeda and that its distance could only mean one thing, and Shapley, upon receiving this letter, understood immediately what it signified: the collapse of the cosmological model he had championed, the opening of a universe so much larger than he had imagined, and he is reported to have remarked to a colleague that here is the letter that destroyed my universe, a poignant acknowledgement of how a single observation can overturn years of careful work and deeply held belief, though it must be said that Shapley accepted the new evidence with grace and went on to make many more contributions to astronomy in the decades that followed. The resolution of the great debate revealed that we inhabit not a single galaxy floating alone in empty space, but one galaxy among billions, each spiral nebula a vast collection of stars comparable to our own Milky Way, the universe transformed from a single island to an archipelago of unimaginable extent, and this realization marked one of the great philosophical transitions in human history, a displacement that echoed the Copernican revolution 3 centuries earlier. For just as Copernicus had shown that Earth was not the center of the solar system, Hubble had shown that our galaxy was not the center of the universe but merely one ordinary galaxy among countless others. Our cosmic significance diminished once again even as our cosmic knowledge expanded. And so we come to rest for a moment in this transformed universe, surrounded by island universes extending in every direction as far as the most powerful telescopes can see, each galaxy containing hundreds of billions of stars, many of those stars orbited by planets, the whole vast structure slowly revealing itself to patient observation and careful measurement, the distances between galaxies measured now in millions of light years, spans of emptiness so profound that light departing a distant galaxy when the first humans walked upon Earth has not yet completed its journey to us, and in contemplating these distances we may feel very small indeed, and yet there is a quiet comfort in knowing that we have found the means to measure even these immensities, that the same techniques of parallax and standard candles that served us for nearby stars have been extended to bridge the gulfs between galaxies, a thread of understanding stretching across the darkness, connecting us to the most distant shores of the cosmic ocean. In the early years of the 20th century, when astronomers were still debating whether the spiral nebulae were nearby clouds of gas or distant collections of stars, a quiet and methodical observer in Arizona began a program of work that would, in time, help reveal something quite unexpected about the nature of the universe itself. Vesto Melvin Slipher worked at the Lowell Observatory in Flagstaff, a small institution founded primarily to study Mars, and he possessed both the patience and the technical skill required to obtain the spectra of faint celestial objects, a task that demanded long exposure times and considerable care. Beginning around 1912 and continuing through to 1917 and beyond, Slipher turned the observatory's 24-inch refractor toward the spiral nebulae, those beautiful pinwheel-shaped patches of light whose true nature remained a matter of some disagreement, and he began the painstaking work of spreading their light into rainbows of color so that he might study the precise wavelengths of the light they emitted. What Slipher found, gradually accumulating results over those quiet years of observation, was rather peculiar. The spectral lines in the light from these spiral nebulae, the characteristic fingerprints left by elements like hydrogen and calcium, were not quite where laboratory measurements said they ought to be. In most cases, the lines were shifted toward the red end of the spectrum, stretched to longer wavelengths, and the degree of this stretching implied that the nebulae were moving away from the Earth at remarkable speeds, sometimes hundreds of kilometers per second, velocities far greater than those of ordinary stars within our own galaxy. By 1917, Slipher had measured the spectra of some 25 spiral nebulae, and of these, the vast majority showed this redward displacement, suggesting a general tendency toward recession. Only a handful were approaching, showing the blueward shift that would indicate motion toward us. The implication seemed to be that, for some reason not yet understood, most of these mysterious objects were rushing away from our corner of space, though what this might mean for the broader structure of the cosmos was not immediately clear, and Slipher himself did not attempt to draw grand theoretical conclusions from his careful measurements. The theoretical framework that would eventually make sense of these observations was being developed, quite independently, in the realm of mathematical physics. Albert Einstein had published his general theory of relativity in 1915, providing a new understanding of gravity not as a force acting at a distance but as a curvature of spacetime caused by the presence of mass and energy, and this theory had profound implications for cosmology, the study of the universe as a whole. In 1927, a Belgian priest and physicist named Georges Lemaitre, working in relative obscurity, published a paper in a French-language Belgian journal that would later be recognized as one of the foundational documents of modern cosmology. Lemaitre had independently derived solutions to Einstein's field equations that described an expanding universe, a cosmos in which the very fabric of space was stretching over time, carrying galaxies along with it like raisins in a rising loaf of bread. What made Lemaitre's contribution particularly remarkable was that he went further than pure theory, combining his mathematical framework with the available observational data, including Slipher's redshift measurements and rough estimates of nebula distances, to calculate an actual rate of expansion, arriving at a value not far from what later researchers would obtain. Lemaitre's paper, however, went largely unnoticed by the broader scientific community. It appeared in an obscure publication, the Annales de la Société Scientifique de Bruxelles, which few astronomers outside Belgium would have had occasion to read, and the idea of an expanding universe seemed, to many, rather too radical to accept without more direct observational support. Einstein himself, upon meeting Lemaitre at a conference, reportedly told him that while his mathematics was correct, his physics was abominable. So strong was the resistance to abandoning the notion of a static and eternal cosmos. And so the insight that would transform our understanding of the universe remained, for a time, a quiet voice speaking into an unlistening world, its significance waiting to be recognized. The observations that would bring the expanding universe into the mainstream of astronomical thought came from the Mount Wilson Observatory in California, where Edwin Hubble and his assistant Milton Humason were conducting a systematic survey of the spiral nebulae, now increasingly accepted as independent galaxies far beyond the Milky Way. Hubble, as we have discussed, had already used Cepheid variable stars to establish the distances to some of the nearer galaxies, demonstrating beyond reasonable doubt that they lay millions of light-years away, and now he sought to combine these distance measurements with velocity information derived from the redshifts that Slipher and others had been accumulating. Humason, a former mule driver who had worked his way up from janitor to become one of the most skilled observers in the world, obtained additional spectra with extraordinary patience, sometimes exposing photographic plates for entire nights to capture the faint light of distant galaxies, and together the two men assembled a dataset that would prove to be of historic importance. In 1929, Hubble published a short paper presenting the results of this analysis, and what he found was a relationship of elegant simplicity. When he plotted the recession velocities of galaxies against their distances, the points fell, with some scatter, along a roughly straight line, indicating that more distant galaxies were receding faster in direct proportion to their distance. A galaxy twice as far away was moving away twice as fast, a galaxy 3 times as far away was moving 3 times as fast, and so on. This relationship, which would come to be known as Hubble's law, could be expressed as a simple equation. The velocity of recession equals the distance multiplied by a constant, and the value of this constant, which Hubble estimated from his data, came out to approximately 500 kilometers per second per megaparsec. This meant that for every megaparsec of distance, roughly 3.26 million light-years, a galaxy's recession velocity increased by about 500 kilometers per second. The profound implication of this discovery, an implication that Lemaitre had already articulated theoretically, was that the universe itself was expanding. The galaxies were not flying outward through a static and unchanging space, like shrapnel from an explosion, but rather space itself was stretching, carrying the galaxies along with it, and the farther away a galaxy was, the more intervening space there was to stretch, and therefore the faster it appeared to recede. This was a fundamentally different picture from anything that had come before, a universe not fixed and eternal but dynamic and evolving, a cosmos with a history that might be traced backward in time to some earlier, denser state. The philosophical implications were staggering, though they took time to sink in, and the observational results stood independent of whatever interpretation one might place upon it. The value of the constant in Hubble's law, which would naturally come to be called the Hubble constant, was a matter of considerable uncertainty and would remain so for many decades. Hubble's original estimate of approximately 500 kilometers per second per megaparsec implied a rather young universe, for if one imagined running the expansion backward in time, all the galaxies would have been together at a single point only about 2 billion years ago. This was troublesome because geologists had already established, from radioactive dating of rocks, that the Earth itself was older than 2 billion years, and it seemed rather awkward for the universe to be younger than some of its contents. Something, clearly, was not quite right, and the resolution of this puzzle would require a fundamental revision of the cosmic distance scale. The breakthrough came in 1952, when the German-American astronomer Walter Baade, working at Mount Wilson with the benefit of the wartime blackouts that had darkened Los Angeles and improved observing conditions, made a discovery that would double the estimated size of the universe virtually overnight. Baade found that the Cepheid variable stars used to measure cosmic distances came in 2 distinct populations, with different period luminosity relationships, and that Hubble had been applying the relationship for one type of Cepheid to stars that actually belonged to the other type. The Cepheids in distant galaxies were, on average, intrinsically brighter than Hubble had assumed, which meant they had to be farther away to appear as faint as they did, and when this correction was applied, all the distance estimates had to be roughly doubled. The Andromeda galaxy, which Hubble had placed at about 900,000 light-years, was now recognized to be more than 2 million light-years distant, and the entire scale of the cosmos expanded accordingly. This revision brought the age of the universe into better agreement with geological evidence, but the precise value of the Hubble constant remained a source of ongoing debate and investigation. Alan Sandage, who had been Hubble's last assistant before the great astronomer's death in 1953, and who would go on to become one of the most influential observational cosmologists of the 20th century, devoted much of his career to refining the cosmic distance scale and pinning down a more accurate value for the constant. Sandage's work, conducted over decades with meticulous attention to sources of systematic error, gradually brought the estimated value downward, from Hubble's original 500 toward values in the range of 50 to 100 kilometers per second per megaparsec, and for many years there was a contentious disagreement between researchers who favored values near the lower end of this range and those who favored values near the higher end, a dispute that became rather personal at times, and was not fully resolved until the advent of new observational techniques at the turn of the 21st century. The modern consensus value, established through multiple independent methods including observations of the cosmic microwave background radiation and distant supernovae, places the Hubble constant at approximately 70 kilometers per second per megaparsec, though there remain small but intriguing discrepancies between different measurement techniques that continue to occupy the attention of cosmologists today. There is a certain irony in the fact that Edwin Hubble, whose name is forever attached to the law describing cosmic expansion, never fully accepted the interpretation that the redshifts of galaxies were caused by the expansion of space. Hubble was, above all, an empiricist, deeply committed to the careful collection and analysis of observational data, and he remained cautious about theoretical interpretations that went beyond what the observations strictly required. He preferred to speak of apparent velocities rather than actual recession, and he acknowledged the possibility that the redshifts might have some other explanation, perhaps related to light losing energy over the vast distances it traveled, a hypothesis sometimes called tired light that has since been ruled out by various lines of evidence. Hubble continued to gather data and refine his measurements until his death from a heart attack in 1953, never having fully committed to the expanding universe that bears his legacy, a reminder that the history of science is often more complicated and less triumphant than the simplified accounts might suggest. The recognition of cosmic expansion marked a fundamental turning point in our understanding of the universe, transforming cosmology from a branch of philosophy into an observational science with testable predictions and measurable parameters. The Hubble constant, though it took decades to pin down with confidence, became one of the key numbers characterizing our universe, determining its age, its size, and its ultimate fate. The work of Slipher, Lemaitre, Hubble, Humason, Barter, Sandage, and many others built upon one another in the manner typical of scientific progress, each contribution adding a piece to a larger puzzle, each refinement bringing us closer to a coherent picture of a cosmos not static and unchanging but dynamic and evolving, stretching out through time from some hot dense beginning toward a future that remains, even now, the subject of ongoing investigation and gentle contemplation. When we look out into the universe and ask how far away things are, we find ourselves building a kind of staircase, where each step depends upon the one below it, and where the higher we climb, the more we must trust that our lower steps are solid and true. This is what astronomers call the cosmic distance ladder, and it is perhaps one of the most elegant and painstaking constructions in all of science, assembled over more than a century by patient observers who understood that knowing where we are in the cosmos requires first knowing how far away everything else might be. The idea behind the distance ladder is beautifully simple in principle, even if it proves enormously challenging in practice. We begin with methods that work only for objects very close to us, perhaps stars within our own galaxy that are near enough for us to measure their distances using geometry alone, through the subtle shift in their apparent position as Earth moves around the Sun. These nearby measurements then allow us to calibrate another method, one that works for objects somewhat farther away, and that method in turn calibrates yet another technique that reaches even deeper into space. Each rung of the ladder extends our reach, but each rung also carries with it the accumulated uncertainties of all the rungs below, so that by the time we are measuring distances to the most remote galaxies, we must have tremendous confidence in every step we have taken along the way. Among the most important rungs on this ladder are what astronomers call standard candles, which are objects whose intrinsic brightness we believe we understand well enough that we can determine their distance simply by measuring how bright they appear to us here on Earth. The principle is the same one you might use if you saw a lighthouse beam in the darkness and knew exactly how powerful that lighthouse was supposed to be. For by measuring how dim the light appeared to your eyes, you could calculate how far away you must be standing from its source. The challenge, of course, lies in finding cosmic lighthouses whose true brightness we can reliably determine, objects that shine with a consistent and predictable luminosity regardless of where in the universe they happen to be. The most powerful of these cosmic lighthouses, the ones that allow us to measure distances across truly vast stretches of space, are a particular type of stellar explosion known as Type Ia supernovae. These are not ordinary supernovae of the kind that occur when massive stars exhaust their fuel and collapse under their own weight. Instead, Type Ia supernovae arise in binary star systems where one of the stars is a white dwarf, which is the dense remnant core left behind when a star like our Sun reaches the end of its life and gently sheds its outer layers into space. A white dwarf is an extraordinary object, containing roughly the mass of our Sun compressed into a sphere no larger than the Earth, and it is held up against the crushing force of gravity not by the heat of nuclear fusion but by a quantum mechanical effect related to the behavior of electrons in extremely dense matter. When a white dwarf exists in a close binary system with a companion star, it may gradually draw material from that companion onto its own surface, slowly growing more and more massive over millions of years. There exists, however, a fundamental limit to how massive a white dwarf can become while still supporting itself against gravitational collapse, and this limit was calculated by the Indian-American astrophysicist Subrahmanyan Chandrasekhar in the early 1930s. The Chandrasekhar limit, as it came to be known, is approximately 1.4 times the mass of our Sun, and when a white dwarf approaches this critical threshold, something catastrophic occurs. The density at its core becomes so extreme that carbon and oxygen nuclei begin to fuse in a runaway thermonuclear reaction, and within just a few seconds the entire star is consumed in an explosion of almost unimaginable violence, briefly outshining an entire galaxy of 100 billion stars. The crucial feature of this process, from the perspective of distance measurement, is that all Type Ia supernovae begin from white dwarfs approaching the same critical mass, which means they all release roughly the same amount of energy in their explosions. This consistency in their intrinsic luminosity makes them potentially excellent standard candles, visible across billions of light years and serving as beacons by which we can map the structure of the universe on its grandest scales. The systematic study of supernovae as a distinct class of astronomical phenomena owes much to the work of two astronomers working at the Mount Wilson Observatory in California during the 1930s. Fritz Zwicky, a Swiss astronomer known for his unconventional ideas and sometimes prickly temperament, and Walter Bader, a German astronomer of meticulous observational skill, together laid the foundations for our modern understanding of these stellar explosions. In 1934, Zwicky and Bader published a remarkable paper in which they not only coined the term supernova to describe these extraordinarily luminous stellar outbursts, but also proposed that supernovae might represent the transition of ordinary stars into neutron stars, an idea that seemed almost fantastical at the time but which proved largely correct. Their classification work established the basic framework that astronomers still use today, distinguishing between different types of supernovae based on the chemical signatures present in their light. For many decades, astronomers worked to understand whether Type Ia supernovae were truly uniform enough to serve as reliable standard candles, or whether variations in their brightness might introduce unacceptable errors into distance measurements. The breakthrough came in 1993, when the American astronomer Mark Phillips, working at the Cerro Tololo Inter-American Observatory in Chile, published a paper demonstrating a remarkable relationship between the peak brightness of a Type Ia supernova and the rate at which it subsequently fades from view. Phillips showed that brighter supernovae decline more slowly, fading gradually over many weeks, while fainter ones dim more rapidly. This correlation, which became known as the Phillips relation, transformed Type Ia supernovae from standard candles into what astronomers sometimes call standardizable candles, objects whose intrinsic luminosity can be determined by carefully observing the shape of their light curve as they brighten and then fade. The practical application of this technique was demonstrated through careful observational programs, including the Callan-Tololo supernova survey led by the American astronomer Robert Kirshner and his colleagues. This survey, which operated through the early 1990s, systematically discovered and monitored dozens of Type Ia supernovae in relatively nearby galaxies, establishing the reliability of the Phillips relation and providing a foundation of well-calibrated supernovae against which more distant explosions could be compared. The work was painstaking and required careful attention to photometric accuracy, but it demonstrated that Type Ia supernovae could indeed serve as precise distance indicators reaching far beyond what any previous method had achieved. Yet supernovae are rare events, occurring perhaps once per century in a typical galaxy, and they appear without warning, flare briefly, and then fade forever into darkness. Astronomers therefore require other methods to measure distances to galaxies when no supernova has recently occurred, and several ingenious techniques have been developed to fill this need. In 1977, the astronomers Brent Tully and Richard Fisher published a paper describing a relationship that has since become one of the workhorses of extragalactic distance measurement. They observed that spiral galaxies that rotate more rapidly tend to be more luminous, a correlation that makes physical sense when one considers that more massive galaxies contain more stars and thus shine more brightly, while also possessing stronger gravitational fields that cause their stars and gas to orbit at higher velocities. By measuring the rotation speed of a spiral galaxy, which can be determined from the Doppler shifts in the light emitted by its stars and gas clouds as they move toward us and away from us, astronomers can estimate its intrinsic luminosity and thus calculate its distance. The Tully-Fisher relation has proven remarkably useful for measuring distances to spiral galaxies out to several hundred million light-years, although it requires careful calibration using galaxies whose distances are already known through other means. A year before Tully and Fisher published their result, the astronomers Sandra Faber and Robert Jackson had described a similar relationship for elliptical galaxies, which are spheroidal collections of old stars that do not rotate in the organized fashion of spirals but instead contain stars moving on more randomly oriented orbits. The Faber-Jackson relation connects the luminosity of an elliptical galaxy to the velocity dispersion of its stars, which is a measure of how fast the stars are moving in their scrambled orbits. More luminous elliptical galaxies have higher velocity dispersions, again reflecting the connection between mass, gravitational binding, and total stellar content. Like the Tully-Fisher relation, this technique extends the reach of distance measurement but requires careful calibration and attention to potential systematic variations among different types of elliptical galaxies. For elliptical galaxies that are relatively nearby, another technique becomes available, one based on the subtle graininess that appears in images of these smooth-looking stellar systems. When we photograph an elliptical galaxy, we are capturing the combined light of billions of individual stars, and although we cannot resolve most of these stars as separate points of light, their discrete nature produces tiny fluctuations in the apparent surface brightness from one small patch of the galaxy to another. The closer the galaxy, the fewer stars contribute to each small patch of our image, and thus the more pronounced these fluctuations become, much as a photograph of a beach appears smoother when taken from a great height because more individual grains of sand blend together in each tiny portion of the image. This surface brightness fluctuation method provides distance estimates for elliptical galaxies out to about 100 million light-years, adding another useful rung to the cosmic distance ladder. Yet another technique exploits the remarkable uniformity of planetary nebulae, which are the glowing shells of gas expelled by sun-like stars near the ends of their lives. Within any large galaxy, there are many planetary nebulae at any given time, and studies have shown that the very brightest planetary nebulae in different galaxies all tend to have similar intrinsic luminosities, forming a cutoff in what astronomers call the planetary nebula luminosity function. By identifying the brightest planetary nebulae in a distant galaxy and assuming they shine with approximately the same intrinsic brightness as the brightest examples in our own galaxy, astronomers can estimate the distance to that system. This method works well for galaxies within a few tens of millions of light years and provides a valuable cross-check on other distance measuring techniques. Each of these methods carries its own uncertainties, its own potential for systematic error, and when we stack them one upon another to reach ever greater distances, those uncertainties compound in ways that can be difficult to fully characterize. A small error in the calibration of Cepheid variable stars, for instance, propagates upward to affect our estimates of the distances to galaxies where we have used Cepheids to calibrate type Ia supernovae, and those supernova distances in turn affect our measurements of the most remote reaches of the observable universe. The challenge of controlling these systematic errors has occupied generations of astronomers and continues to motivate ever more careful observations and analyses. One of the most ambitious efforts to anchor the cosmic distance scale came in the 1990s, when the astronomer Wendy Friedman led a program known as the Hubble Key Project, which was one of the primary scientific motivations for building the Hubble Space Telescope itself. The goal of the Key Project was to use Hubble's unprecedented ability to resolve individual stars in relatively distant galaxies to measure the distances to galaxies that had hosted type Ia supernovae, thereby providing a firm calibration for the entire supernova distance scale. By carefully observing Cepheid variable stars in these supernova-hosting galaxies and using the well-established period-luminosity relation to determine their distances, Friedman and her colleagues could anchor the type Ia supernova brightness scale to the more secure foundation of Cepheid measurements. The Key Project required years of careful observation and analysis, examining dozens of galaxies and measuring the periods and brightnesses of hundreds of Cepheid variables, all while accounting for the effects of interstellar dust, chemical composition variations, and other potential sources of systematic error. When the results were finally published, they provided what was at the time the most precise measurement of the cosmic distance scale and the expansion rate of the universe, establishing a framework that continues to guide cosmological research today. And so the distance ladder stands, a carefully constructed framework reaching from our nearest stellar neighbors out to the most distant galaxies we can observe, each rung calibrated against the one below, each technique cross-checked against the others wherever possible, all of it representing the patient accumulation of knowledge by astronomers who understood that the universe reveals its secrets slowly, and only to those who ask their questions carefully and wait patiently for the answers, to emerge from the gentle light of distant stars. In the closing years of the 20th century, astronomers found themselves engaged in a quiet race to answer one of the most fundamental questions about our universe, which was whether the expansion that Hubble had discovered all those decades earlier was gradually slowing down, as nearly everyone expected it must be, or whether something else entirely was occurring in the vast reaches of space between the galaxies. Two teams, working independently and sometimes in friendly competition, set out to measure the distances to the most remote type Ia supernovae they could find, hoping that these brilliant stellar explosions might reveal the rate at which cosmic expansion was decelerating, and in doing so, they stumbled upon a discovery that would overturn our understanding of the universe's fate and earn them the highest honor in physics. The Supernova Cosmology Project, based at the Lawrence Berkeley National Laboratory in California and led by a patient and methodical physicist named Saul Perlmutter, had been searching for distant supernovae since the late 1980s, developing techniques to find these rare events in a systematic way rather than simply waiting for them to appear by chance. Meanwhile, the High-Z Supernova Search Team, which was initially led by the Australian astronomer Brian Schmidt and included the American researcher Adam Rees among its key members, had formed in the mid-1990s with the explicit goal of measuring cosmic deceleration using the same standard candle approach. Both teams understood that type Ia supernovae, with their remarkable consistency in peak brightness, offered the best hope of measuring distances to galaxies so remote that their light had been traveling toward us for billions of years, and both teams expected that their measurements would simply confirm what nearly every cosmologist already believed. The reasoning seemed straightforward and almost inevitable. The universe, filled as it was with matter, should be experiencing a gradual slowing of its expansion due to the mutual gravitational attraction of all the galaxies and dark matter distributed throughout space. Gravity, after all, is always attractive, always pulling things together, and so the expansion that began with the Big Bang should have been decelerating ever since, like a ball thrown upward gradually losing speed as Earth's gravity works against its motion. The only question seemed to be how quickly this deceleration was occurring, which would determine whether the universe would eventually stop expanding and collapse back upon itself in a big crunch, or whether it would expand forever but at an ever-diminishing rate. The supernovae would provide the answer, or so everyone thought. To measure the deceleration, astronomers needed to compare the brightness of distant supernovae with their redshifts, which indicate how much the universe has expanded during the time their light has been traveling toward us. If the universe were decelerating, then supernovae at very great distances, whose light was emitted billions of years ago when the universe was expanding more quickly, should appear slightly brighter than one would expect based on their redshifts alone, because the faster past expansion would have carried them to somewhat smaller distances than a uniformly expanding universe would predict. Conversely, if the universe were accelerating, which almost no one seriously considered, then distant supernovae should appear fainter than expected, because the increasing expansion rate would have carried them to even greater distances. The team set about gathering their data with care and precision, calibrating their instruments, accounting for the dimming effects of dust, and measuring the brightnesses and redshifts of dozens upon dozens of distant type Ia supernovae. When the results began to come in, both teams found something deeply puzzling, something that seemed at first like it must be an error in their measurements or their analysis. The distant supernovae were not slightly brighter than expected, as a decelerating universe would predict, but were instead noticeably fainter, by roughly 25% on average, than they should have been if cosmic expansion were slowing down. This was precisely backward from what gravity should be doing, and the teams initially searched for explanations that did not require abandoning the decelerating model that everyone had assumed was correct. Perhaps there was some unknown form of dust in intergalactic space that was dimming the light from distant supernovae without reddening it in the usual way. Perhaps type Ia supernovae had been intrinsically different in the early universe, producing less light than their modern counterparts. Perhaps there were systematic errors in the measurements that had somehow escaped detection. Yet as both teams refined their analysis and gathered more data, checking and rechecking their work with the meticulous care that extraordinary claims require, the conclusion became increasingly difficult to avoid. The distant supernovae were fainter because they were farther away than expected, and they were farther away because the expansion of the universe was not slowing down but speeding up. Something was pushing the galaxies apart with increasing vigor, counteracting and indeed overwhelming the attractive force of gravity on the larger scales. In 1998, both teams published their findings, the Supernova Cosmology Project and the High-Z Supernova Search Team arriving independently at the same revolutionary conclusion, which lent considerable weight to a result that might otherwise have seemed too strange to believe. The universe was accelerating, and no one knew why. The unknown cause of this cosmic acceleration was given the placeholder name of dark energy, a term that acknowledged our profound ignorance about what was actually driving the phenomenon while allowing astronomers and physicists to discuss it in a consistent way. Analysis of the supernova data, combined with other cosmological measurements, suggested that this dark energy constituted approximately 68% of the total energy content of the universe, making it by far the dominant component of the cosmos, even though we cannot see it, touch it, or directly detect it in any laboratory experiment. Ordinary matter, the stuff of which stars and planets and people are made, accounts for only about 5% of the universe's energy budget, with dark matter making up roughly 27%, and so the substance we understand best and encounter most directly in our daily lives turns out to be a small minority of what the universe actually contains. The discovery also brought renewed attention to an old idea that Albert Einstein had introduced and then abandoned in the years following his development of general relativity. When Einstein had applied his equations to the universe as a whole, he had found that they predicted either expansion or contraction, but not the static, unchanging cosmos that was then believed to exist. To avoid this implication, Einstein had introduced a term called the cosmological constant, represented by the Greek letter lambda, which acted as a kind of repulsive force that could balance gravity and maintain a static universe. When Hubble's observations revealed that the universe was indeed expanding, Einstein reportedly called the cosmological constant his biggest blunder and abandoned it entirely. Now, more than 70 years later, the supernova observations suggested that something very much like the cosmological constant might actually exist, providing exactly the kind of repulsive effect that could cause cosmic expansion to accelerate rather than decelerate. Einstein's blunder, it seemed, might not have been a blunder at all, though whether dark energy is truly the cosmological constant or something else entirely remains an open question. The significance of this discovery was recognized in 2011, when the Nobel Prize in Physics was awarded jointly to Saul Perlmutter for the Supernova Cosmology Project and to Brian Schmidt and Adam Rees for the High-Z Supernova Search Team, honoring all three scientists for their leadership in the observations that had revealed the accelerating expansion of the universe. It was a fitting recognition of work that had fundamentally changed our picture of the cosmos, transforming dark energy from an idea that had been briefly considered and then forgotten into the dominant component of the universe's energy content. In the years following the initial discovery, additional surveys were undertaken to confirm and refine the supernova measurements, ensuring that such a surprising result was truly robust. The ESSEN survey, which stood for Equation of State, Supernovae Trace Cosmic Expansion, observed distant Type Ia supernovae over several years using telescopes in Chile, gathering a carefully calibrated sample that could test whether the original findings held up under further scrutiny. The Supernova Legacy Survey, often abbreviated as SNLS, conducted an even larger program using the Canada-France-Hawaii telescope, discovering hundreds of distant supernovae and measuring their properties with great precision. These follow-up surveys consistently confirmed the accelerating expansion, showing that the original discovery was not a statistical fluke or the result of some overlooked systematic error, and they allowed astronomers to constrain the properties of dark energy with increasing accuracy. As measurements have become more precise, however, a curious tension has emerged between the expansion rate derived from supernova observations and that inferred from the cosmic microwave background radiation, which is the faint afterglow of the Big Bang that permeates all of space. When astronomers measure the distances and redshifts of supernovae in the relatively nearby universe, and when they combine these with other local measurements such as Cepheid variables and the tip of the red giant branch, they obtain a value for the current expansion rate that is somewhat higher than what the cosmic microwave background observations predict, assuming our standard model of cosmology is correct. This discrepancy, sometimes called the Hubble tension, is small in absolute terms but statistically significant, and it has persisted even as both local and cosmic microwave background measurements have become more refined. Whether this tension reflects some unknown systematic error in one or both sets of measurements, or whether it points to new physics beyond our current understanding, remains an active area of research, one that continues to occupy the attention of cosmologists around the world. The discovery of cosmic acceleration also carried profound implications for the ultimate fate of the universe, changing the predicted ending from one scenario to another entirely. In a universe where expansion was decelerating, there were two possibilities. Either the expansion would eventually halt and reverse, leading to a big crunch in which all matter collapsed back together, or the expansion would continue forever but at a diminishing rate, with the universe gradually approaching a static state. The accelerating expansion changed this picture dramatically, because if dark energy continues to drive cosmic acceleration indefinitely, then the expansion of the universe will never stop or slow down but will instead continue to speed up forever. Galaxies that are now receding from us will recede ever faster, eventually crossing a cosmic horizon beyond which their light can never reach us, and the observable universe will become increasingly empty and dark as galaxy after galaxy disappears from view. In the very distant future, trillions upon trillions of years from now, the universe will approach a state of maximum entropy, a cold and empty darkness in which no further change is possible, a condition sometimes called the heat death of the universe. This is, perhaps, a melancholy ending to contemplate, though it is so unimaginably far in the future that it need not trouble us as we rest here in the present moment. What matters for our gentle purposes tonight is the remarkable chain of reasoning that led to this understanding, the way in which careful measurements of stellar explosions in distant galaxies revealed the existence of something that constitutes more than two-thirds of everything that is, and yet remains almost completely mysterious. The standard candles that astronomers had worked so hard to calibrate, the Type Ia supernovae whose peak brightness could be determined with such reliability, turned out to be the key that unlocked this particular cosmic secret, showing us that the universe holds surprises even after centuries of careful observation. The story of dark energy is, At its heart, a story about distance measurement, about the patient work of comparing how bright something appears with how bright it actually is, and about what we learn when reality refuses to match our expectations. It reminds us that the universe is under no obligation to behave as we think it should, and that our best theories, however successful they may be in some domains, are always provisional, always subject to revision in light of new evidence. The astronomers who set out to measure cosmic deceleration found cosmic acceleration instead, and in doing so, they discovered that most of the universe is made of something we do not understand. This is a humbling thought, but also a reassuring one, for it means that there are still mysteries to be explored, still discoveries to be made, still questions that patient observation may one day answer, even if we ourselves will not be awake to hear those answers tonight. And so we arrive at a time when the ancient art of measuring stellar positions, the discipline that astronomers call astrometry, left the surface of the Earth entirely and rose above the trembling atmosphere that had limited our vision for so many centuries, and in doing so transformed our understanding of where the stars actually are, not approximately, not within acceptable margins of uncertainty, but with a precision that earlier generations could scarcely have imagined possible. For as long as telescopes had pointed upward from observatories perched on mountaintops and nestled in valleys, astronomers had contended with a fundamental obstacle that no amount of engineering ingenuity could fully overcome, and that obstacle was the atmosphere itself, the very air that we breathe and that makes our planet hospitable to life, which also happens to be in constant subtle motion, with cells of warmer air rising and cooler air descending, with winds at various altitudes sliding past one another, with moisture condensing and evaporating, and all of this turbulence causes the light from distant stars to bend and shimmer in ways that blur their positions ever so slightly, which is the same phenomenon that makes stars appear to twinkle so charmingly on a clear night, though that twinkling represents a serious impediment to anyone trying to measure exactly where a star sits against the backdrop of more distant stars. Ground-based parallax measurements, even those conducted with the finest instruments and the most meticulous techniques, had reached a kind of ceiling by the middle of the 20th century, achieving accuracies of perhaps 50 milliarcseconds under the best conditions, which sounds impressively small until you consider that this level of precision limited reliable distance measurements to stars within roughly 60 or 70 light-years of the Sun, a volume of space containing only a few hundred stars, which is a rather modest sample when one wishes to understand the structure and dynamics of an entire galaxy containing hundreds of billions of stellar inhabitants. The solution, obvious in principle but enormously challenging in practice, was to place a telescope in space, above the atmosphere entirely, where the air could not interfere with the steadiness of stellar images, and where measurements could be made with a precision limited only by the quality of the optics and the stability of the spacecraft itself. And the European Space Agency undertook precisely this ambitious endeavor with a satellite they named Hipparcos, an acronym that stood for High Precision Parallax Collecting Satellite, though the name was also chosen as an affectionate tribute to the ancient Greek astronomer Hipparchus, who had compiled the first comprehensive star catalogue some 2,000 years earlier using nothing more than his own careful eyes and simple instruments. The Hipparcos satellite was launched in August of 1989, and although its intended geostationary orbit was not achieved due to a failure of the booster rocket meant to lift it to that higher altitude, the mission controllers and scientists adapted their plans with remarkable flexibility, working with the elliptical orbit the satellite actually occupied and ultimately extracting scientific results that met or exceeded the original objectives, which serves as a gentle reminder that even in the most technologically sophisticated endeavors, things do not always proceed according to plan, and success often depends upon the ability to adjust and persevere. The man who led the scientific aspects of this mission was Michael Perryman, an astronomer whose dedication to the project spanned decades, from the early planning stages through the launch and operations and the painstaking analysis of the data that followed, and his steady guidance helped ensure that Hipparcos would fulfill its promise of revolutionizing our knowledge of stellar distances. A revolution that unfolded quietly in the form of catalogues and databases rather than dramatic announcements, which is often how the most profound scientific advances actually occur. Over the course of its operational lifetime, which extended from 1989 to 1993, the Hipparcos satellite measured the positions, parallaxes, and proper motions of approximately 118,000 stars, achieving a precision of about 1 milliarcsecond, which represented an improvement of roughly a factor of 50 over what could be accomplished from the ground. And this improvement extended the reliable reach of the parallax method from a few dozen light-years to roughly 1,000 light-years, encompassing millions of stars and including many of the bright and familiar stars that populate our night sky, stars whose distances had previously been estimated only through indirect methods of varying reliability. The data from Hipparcos revealed that some stars were closer than previously thought, while others were more distant, and these revisions rippled outward through the entire framework of cosmic distance measurement, since the parallax distances to nearby stars serve as the foundation upon which all other distance estimates ultimately rest, and if the foundation shifts, even slightly, the entire structure built upon it must be adjusted accordingly. One particularly notable example of such a revision involved the Pleiades, that beautiful cluster of young blue stars visible to the naked eye in the constellation of Taurus, which has been known and admired since ancient times and which many cultures have incorporated into their mythology and navigation, and ground-based measurements had placed this cluster at a distance of approximately 440 light-years. But when the Hipparcos data were analyzed, they suggested a significantly shorter distance of about 390 light-years, a discrepancy of roughly 50 light-years that caused considerable discussion and some controversy among astronomers, since the Pleiades distance affects our understanding of how stars of various masses evolve over time, and getting it wrong would propagate errors into many other areas of astrophysics. The resolution of this Pleiades distance controversy would eventually come from even more precise measurements, but the debate itself illustrated both the power and the limitations of the new space-based astrometry, and reminded the scientific community that even dramatic improvements in precision do not eliminate all sources of uncertainty, and that careful cross-checking between different methods remains essential to building a reliable picture of cosmic distances. Following the success of Hipparcos, the European Space Agency began planning an even more ambitious successor mission, one that would improve upon the precision of Hipparcos by another factor of roughly 100, extending the reach of direct parallax measurements to the far side of our galaxy and measuring not thousands but billions of stars. A project so vast in scope that it required decades of preparation and the development of entirely new technologies for detecting and processing such enormous quantities of astronomical data. This successor mission was given the name Gaia, evoking the ancient Greek personification of the Earth, though the satellite would spend its operational life far from Earth at a gravitationally stable point known as the second Lagrange point, located about 1.5 million kilometers from our planet in the direction away from the Sun, where it could observe the sky continuously without the periodic eclipses that would occur in an orbit closer to Earth. Gaia was launched in December of 2013 and began its scientific observations in July of the following year, carrying two telescopes that point in directions separated by a fixed angle of 106.5 degrees, allowing the satellite to measure the angular separations between stars in widely different parts of the sky with extraordinary precision, and the entire spacecraft rotates slowly, completing one full rotation every 6 hours, while the spin axis itself precesses around the Sun, completing one full precession cycle every approximately 63 days, and this carefully choreographed scanning pattern ensures that every star in the sky is observed multiple times from multiple angles over the course of the mission, building up the vast network of measurements needed to construct a three-dimensional map of stellar positions. The precision achieved by Gaia is measured not in milliarcseconds but in microarcseconds, with the best measurements reaching uncertainties of only a few tens of microarcseconds, which is small enough to detect the parallax of stars tens of thousands of light-years away, well beyond the center of our Milky Way galaxy, and this represents an improvement over ground-based measurements of roughly a factor of several thousand, a transformation so dramatic that it has opened entirely new avenues of astronomical research that would have been impossible with any previous generation of instruments. The data from Gaia are released to the scientific community and the public in periodic installments, with each release incorporating more observations and more sophisticated processing than the last, and the third major data release, known simply as Data Release 3, was made available in June of 2022, containing positions, parallaxes, and proper motions for approximately 1.8 billion stars, along with additional information about stellar brightness, color, temperature, and chemical composition for substantial subsets of these stars, constituting the most detailed and comprehensive census of our galaxy ever compiled. With this extraordinary dataset, astronomers have been able to trace the structure of the Milky Way in unprecedented detail, mapping the spiral arms and the central bar and the halo of ancient stars that surrounds the disk, and they have discovered numerous stellar streams, which are the stretched-out remnants of smaller galaxies and star clusters that have been pulled apart by the gravitational tides of the Milky Way over billions of years. And by studying these streams, researchers are conducting a kind of galactic archaeology, piecing together the history of how our galaxy grew and evolved through the accretion of smaller systems over cosmic time. The Gaia data have also contributed to the detection and characterization of thousands of binary star systems, including some in which one member is a black hole or neutron star, invisible in ordinary light but revealed by its gravitational influence on a visible companion. And there is even the possibility that the subtle wobbles in stellar positions caused by passing gravitational waves might eventually be detectable in the Gaia dataset, opening yet another window onto the universe, though this remains a topic of ongoing investigation rather than established fact. While Gaia has transformed optical astrometry, radio astronomers have achieved comparable precision through a completely different technique known as very long baseline interferometry, or VLBI, which involves linking radio telescopes separated by thousands of kilometers, sometimes on different continents, and combining their signals to create a virtual telescope with an effective diameter equal to the distance between the individual dishes. And this technique can achieve angular resolutions, measured in microarcseconds, rivaling or even exceeding the precision of space-based optical measurements. Radio sources that emit at microwave frequencies through a process called masing, which is similar to the stimulated emission that produces laser light but occurring naturally in clouds of certain molecules around stars and in galactic nuclei, are particularly well suited to VLBI observations because their emission is extremely compact and intense, producing bright point-like sources whose positions can be measured with exquisite precision. One of the most important applications of this technique has been the measurement of the distance to a galaxy called NGC 4258, also known as Messier 106, which lies in the constellation of Canes Venatici and hosts a particularly active nucleus surrounded by a disk of gas that contains water mazes orbiting the central supermassive black hole, and by tracking the motions of these mazes over several years, astronomers have been able to measure both their orbital velocities and their proper motions across the sky, which together yield a geometric distance to the galaxy of approximately 23 million light-years, completely independent of any assumptions about stellar brightness or cosmic expansion. This geometric maser distance to NGC 4258 serves as a crucial anchor point for the extragalactic distance scale, providing a calibration check on other methods such as Cepheid variables and supernovae that are used to measure distances to more remote galaxies, and any systematic errors in those methods would show up as discrepancies with the maser distance. So the agreement that has been found provides reassurance that the cosmic distance ladder, built up painstakingly over more than a century, rests on reasonably solid foundations. And so the measurement of cosmic distances, which began with simple estimates of the Earth size and the Moon's distance in ancient times, has grown into a sophisticated enterprise employing satellites in space and networks of radio telescopes spanning the globe, achieving precisions that would have seemed like fantasy to the astronomers of earlier generations, and yet the fundamental goal remains the same as it always was: to know where things are, to construct a map of the universe that tells us not only what exists but how far away it all lies, and this knowledge, accumulated gradually through the patient work of countless individuals over many centuries, forms the foundation upon which our entire understanding of the cosmos is built. And so we come now to the present day, and perhaps more interestingly, to what lies just ahead, to the techniques that astronomers are developing even now as you settle in for sleep, and to the mysteries that remain stubbornly unresolved despite all the ingenuity and patience that has been brought to bear on the question of cosmic distances. For it turns out that the universe, as is so often the case, has not quite surrendered all its secrets, and there exists at this very moment a puzzle at the heart of our distance measurements that has kept cosmologists occupied for the better part of a decade, a puzzle that some believe may point toward entirely new physics, though others maintain that the explanation will prove to be something more mundane, a systematic error perhaps, or an overlooked calibration issue, and the debate continues in a quiet and methodical way, as scientific debates tend to do when given sufficient time and data. This puzzle has come to be known as the Hubble tension, and it concerns a rather troubling disagreement between two different methods of measuring the expansion rate of the universe, that number we call the Hubble constant, which tells us how fast galaxies are receding from one another for every megaparsec of distance between them. When astronomers measure this constant using what we might call local methods, building up the cosmic distance ladder rung by rung from parallax to Cepheids to Type Ia supernovae, they arrive at a value of approximately 73 kilometers per second per megaparsec. This is a number that has been refined over many years by various teams, most notably the SH0ES collaboration, which stands for supernova H0 for the equation of state, a somewhat awkward acronym but one that has become synonymous with the most careful and thorough application of the distance ladder method. Their measurements have been checked and rechecked, their calibration scrutinized and improved, and yet the number stubbornly remains in the vicinity of 73. But here is where the tension arises, and it is a gentle sort of tension as these things go, the kind that keeps theorists thinking and observers observing without causing anyone undue alarm. When cosmologists look instead at the cosmic microwave background, that faint afterglow of the Big Bang that pervades all of space, they can extract from it subtle patterns of prediction for what the Hubble constant ought to be. The European Space Agency's Planck satellite mapped this background radiation with extraordinary precision, measuring temperature fluctuations of just a few parts in 100,000, and from these measurements, combined with our best understanding of how the universe evolved from that early era to the present day, a rather different value emerges, approximately 67 kilometers per second per megaparsec. The difference between 67 and 73 may not seem terribly large, just 8 or 9%, but both measurements claim uncertainties of only 1 or 2%, which means that if both are correct, there is a genuine discrepancy that cannot be explained by measurement error alone. The James Webb Space Telescope, that magnificent infrared observatory that was launched in late 2021 and began science operations in 2022, was hoped by many to help resolve this tension. Its infrared capabilities are particularly well suited to observing Cepheid variable stars in distant galaxies, because infrared light is less affected by dust than visible light, and dust has always been one of the nagging sources of uncertainty in distance ladder measurements. The early observations from Webb have indeed provided clearer and sharper images of Cepheids than were ever possible with the Hubble Space Telescope, and the SH0ES team has used this new data to refine their measurements further. But rather than resolving the tension, these initial results have if anything deepened it, confirming the higher value of around 73 with even greater confidence than before, which suggests that the discrepancy is unlikely to be explained by problems with how we observe Cepheids, and so the mystery remains, quietly persistent, neither solved nor forgotten. There are, of course, ways to measure cosmic distances that bypass the traditional distance ladder entirely, and one of the most exciting of these involves gravitational waves, those ripples in the fabric of spacetime that Einstein predicted over a century ago and that were first directly detected in September 2015 by the LIGO observatories in the United States. Gravitational waves are produced when massive objects accelerate, and the most powerful sources are the mergers of compact objects like black holes and neutron stars, events so violent that they shake the very geometry of space itself. What makes gravitational waves useful for cosmology is that they carry within them, encoded in the amplitude and frequency of the signal, information about the distance to the source, without requiring any intermediate calibration steps. For this reason, they have been called standard sirens, a lovely acoustic metaphor that echoes the astronomical term standard candles. The first truly useful standard siren for cosmology came on the 17th of August, 2017, when both LIGO and its European counterpart Virgo detected the gravitational waves from two neutron stars spiraling inward and merging. This event, designated GW170817, was special not only because it was detected in gravitational waves, but because it was also observed across the electromagnetic spectrum, from gamma rays to radio waves, allowing astronomers to identify the host galaxy and thus obtain an independent measure of the redshift. By combining the gravitational wave distance with the electromagnetic redshift, a measurement of the Hubble constant was obtained that was completely independent of both the distance ladder and the cosmic microwave background. The precision of this single measurement was not yet sufficient to definitively favor one value over the other, but it represented a proof of concept, a demonstration that an entirely new method had arrived. And as more such events are detected in the coming years, the standard siren technique will provide an increasingly valuable cross-check on other methods. Looking further into the future, there are space missions being planned that will push the boundaries of what is possible in measuring cosmic distances. NASA's Nancy Grace Roman Space Telescope, named after the astronomer who was instrumental in developing the Hubble Space Telescope, is scheduled for launch in the mid-2020s and will conduct wide-field surveys designed in part to discover and characterize thousands of Type Ia supernovae. By observing so many supernovae across such a large volume of space, Roman will help to reduce the statistical uncertainties in our understanding of cosmic expansion and will search for subtle variations that might reveal whether the Hubble constant has changed over time, or whether the supernovae themselves might be behaving in unexpected ways that could explain the tension. It is the kind of patient, methodical survey work that has historically yielded the greatest advances in our understanding, even if it lacks the dramatic flair of a single spectacular discovery. Even more ambitious in some ways is a proposed mission called THEIA, which would achieve astrometric precision at the level of microarcseconds, far surpassing what was possible with Hipparcos or even Gaia. At such exquisite precision, parallax measurements could be extended to distances of tens of kiloparsecs, reaching throughout the Milky Way and even into the nearest external galaxies, providing a vastly expanded foundation for the distance ladder. K remains at this point a concept under study rather than an approved mission, but it represents the direction in which the field is heading, toward ever greater precision and ever more reliable calibrations of the techniques that underpin our knowledge of cosmic distances. Another approach that has gained considerable attention in recent years involves the use of strong gravitational lensing, a phenomenon in which light from a distant quasar is bent and split into multiple images by the gravity of a foreground galaxy. Because the light in each image travels along a different path through the gravitational field, it arrives at Earth at slightly different times, and by monitoring the brightness variations of the quasar and measuring the time delays between images, astronomers can infer the distances involved. This technique, like gravitational wave standard sirens, provides a measurement of the Hubble constant that is independent of the traditional distance ladder, and various teams have been working to refine it and reduce the systematic uncertainties. The results so far have tended to favor values somewhere between the high and low measurements, adding another piece to the puzzle without yet completing it. Meanwhile, the SH0ES team continues its ongoing refinements, making use of both the Hubble Space Telescope and the James Webb Space Telescope to improve every link in the distance ladder. They have extended their Cepheid observations to more galaxies. They have refined their understanding of how Cepheid brightness depends on chemical composition, and they have worked to reduce every source of systematic error that could possibly explain the discrepancy. Their persistence is a testament to the scientific method at its best, a willingness to keep pushing and probing even when the answer refuses to come easily, and their work will undoubtedly continue for many years to come. Baryon acoustic oscillations represent yet another cosmic ruler that astronomers have learned to read, a relic of sound waves that propagated through the early universe in the first few 100,000 years after the Big Bang. These waves left their imprint on the distribution of matter, creating a characteristic scale that can be measured in the clustering of galaxies. And because this scale is known from theoretical calculations, it can be used as a standard ruler to infer distances at various epochs. Like the cosmic microwave background, baryon acoustic oscillations tend to favor the lower value of the Hubble constant, around 67, which deepens the mystery rather than resolving it, and suggests that the tension may reflect something fundamental about the universe rather than a simple measurement error. And so we arrive at a philosophical question, one that does not have a definitive answer but which is nonetheless worth contemplating as you drift off to sleep. Will we ever achieve 1% precision on cosmic distances? And more importantly, what mysteries might such precision reveal? The history of astronomy teaches us that improved precision has a way of uncovering new phenomena, that what appears at first to be a mere discrepancy often turns out to be a window into something deeper and more interesting. The anomalous precession of Mercury's orbit, for instance, was a minor puzzle in celestial mechanics until Einstein showed that it was a consequence of general relativity, a clue that our understanding of gravity itself was incomplete. Perhaps the Hubble tension will prove to be something similar, a hint that there is new physics waiting to be discovered, perhaps a previously unknown particle, or a modification to our understanding of dark energy, or something we have not yet imagined. Or perhaps, and this is equally possible, the tension will eventually be resolved by some subtle systematic effect that we have not yet identified, and the two values will converge as our measurements improve. Either outcome would represent progress, either a deeper understanding of the universe or a more complete mastery of our observational techniques, and both are worth pursuing with the same patient diligence that has characterized the measurement of cosmic distances from the very beginning. What is certain is that the work will continue, that new telescopes will be built and launched, that new techniques will be developed and refined, and that the human desire to know how far away the stars really are will remain undiminished. It is a slow and painstaking endeavor, this measurement of the cosmos, and it does not lend itself to quick answers or dramatic breakthroughs, but rather to the gradual accumulation of knowledge over decades and centuries. And perhaps there is something comforting in that, in the thought that long after we are gone, astronomers will still be gazing up at the night sky, still refining their distance measurements, still pushing the boundaries of what is known just a little bit further into the unknown.